Imagine waking up on Mars, not in a pressurized habitat, but outside, breathing normally, walking across rust-colored dust under a butterscotch sky. The sun is smaller than it appears from Earth, casting long shadows across ice-covered rocks. This moment, actual human boots on actual Martian dirt, is not fantasy. It's engineering. It's a problem to be solved. But Mars is just the beginning. Beyond Mars lie the giant planets, their moons, and then the truly incomprehensible distances. Alpha Centauri at 4.25 light years away. Andromeda at 2.5 million light years. The Virgo supercluster spanning 100 million light years. The question that drives space exploration is simple. How far can we go? The answer depends on physics, technology, biology, and willpower. It depends on whether we're asking about Mars or Proxima Centauri. It depends on what timescales we're willing to accept. It also depends on understanding exactly how vast space truly is, a lesson that humbles every space explorer. Let me start by confronting the scale. Earth to the moon is 380,000 kilometers. That's a distance that took humans 3 days to cross in 1969. The Apollo spacecraft traveled at roughly 40,000 kilometers per hour, the fastest speeds humans have ever achieved. Mars is closer to home than Jupiter. At its nearest approach, Mars is 54 million kilometers away. At its farthest, 401 million kilometers. A spacecraft traveling at Apollo speeds would take several years to reach Mars. But wait, a spacecraft can't maintain Apollo speeds for years. Rockets accelerate to speed, then coast. The gravity of Earth, Sun, and other planets constantly tugs on the spacecraft, altering its trajectory. The spacecraft has to follow an orbital path called a Hohmann transfer orbit, an elliptical path that minimizes fuel consumption by using the Sun's gravity efficiently. This path takes 6 to 9 months to Mars. In 1965, Mariner 4 became the first spacecraft to reach Mars. It took more than 7 months. In 1971, Mariner 9 reached Mars and became the first spacecraft to orbit another planet. In 1976, Viking 1 became the first spacecraft to land on Mars and transmit data from the surface. These missions were extraordinary achievements. They required solving problems no one had solved before, but they used 1960s technology. Modern spacecraft are faster and more capable, but they're still limited by the same physical laws that govern Mariner 4. The fastest spacecraft ever launched is the Parker Solar Probe, designed to study a sun. It reaches speeds exceeding 600,000 kilometers per hour. That's about 15 times faster than Apollo. But the Parker Solar Probe is falling toward the sun. Its speed comes from falling into a massive gravitational well. To reach another star, a spacecraft would need a completely different approach. Let me break down the problem of interplanetary travel. To travel from Earth to another planet, you need to, first, escape Earth's gravity. This requires reaching what's called escape velocity, about 11 kilometers per second. Second, enter an orbit that intersects both Earth's orbit and your destination planet's orbit. The most fuel-efficient path is the Hohmann transfer orbit. Third, time your departure so that when your spacecraft arrives, the destination planet is actually there. Fourth, decelerate when you arrive, so you enter orbit or land instead of zooming past at high speed. Fifth, have enough fuel, supplies, and equipment for the journey. The first crewed mission to Mars will probably take about 9 months to get there. The astronauts will need life support systems that provide breathable air for 9 months, then a year on the surface, then 9 months returning. That's about 2 years total. The systems need to recycle water and air with incredible efficiency, radiation shielding to protect against cosmic rays and solar radiation. Earth's magnetic field shields us. Mars doesn't have one. Astronauts will receive radiation doses that increase cancer risk. Food for 2 years, or a spacecraft with hydroponic systems and enough equipment to grow food. Fuel for landing, conducting surface operations, and returning to Earth orbit. This requires either bringing all the fuel from Earth or finding fuel on Mars. Using local fuel sources dramatically reduces the amount you need to launch from Earth. Psychological preparation for isolation, danger, and confined spaces for 2 years. The mental challenge might be as hard as the physical one. Once humans land on Mars, the mission becomes focused. They have limited time on the surface, months, maybe a year, before they need to return. But Mars isn't the only destination. Venus is closer to Earth than Mars most of the time. Distances to Venus range from 38 million to 261 million kilometers, depending on orbital positions. However, Venus is a nightmare to land on. The surface temperature is 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure is 90 times Earth's, equivalent to being 900 meters deep in the ocean. The atmosphere is 96% carbon dioxide with clouds of sulfuric acid. No human has ever landed on Venus. No robotic lander has survived more than 127 minutes on the surface. Every spacecraft sent to Venus has been crushed and melted. Venus is unlikely to be a destination for human settlement, though scientists continue designing landers that might survive long enough for research. The Moon is different. At 380,000 kilometers, it's close enough for quick missions. A spacecraft reaches the Moon in 3 days. The Moon is where humans will likely establish a permanent base, not as an end goal, but as a stepping stone to Mars. A lunar base would serve as a testing ground for Mars technology. Astronauts could spend months on the Moon, testing life support systems, growing food, operating heavy equipment, working with robots. The Moon also has water ice at the poles. Extracting this water provides drinking water and allows splitting the water into hydrogen and oxygen, rocket fuel. A lunar fuel depot would dramatically reduce the cost of Mars missions. Instead of launching all fuel from Earth, spacecraft would dock at the Moon, refuel, then proceed to Mars with much lighter initial launch weights. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, establishing a sustainable presence by the 2030s. Private companies like SpaceX are also working on lunar architecture. SpaceX's Starship is designed to land on the Moon and refuel there. Once humans establish a presence on the Moon, Mars becomes feasible. The first crewed Mars mission is probably a decade away. Most estimates put human landing on Mars sometime in the 2030s or 2040s, depending on funding and technological progress. Multiple organizations are planning Mars missions. NASA's plan involves the Space Launch System and Orion spacecraft. SpaceX is developing Starship specifically for Mars. International partners and private companies worldwide are working on pieces of the puzzle. The challenge is primarily economic, not technological. The physics of reaching Mars is understood. The engineering is difficult but solvable. The cost is enormous, likely hundreds of billions of dollars. But it's possible. Within your lifetime, humans could be walking on Mars. The logistics are complex. A Mars mission requires a heavy-lift launch vehicle to get the spacecraft off Earth. SpaceX's Starship is designed for this. a spacecraft capable of keeping humans alive for 2 years in space. Estimates suggest mission costs of several $100 billion for developing the necessary vehicles. Supplies: food, water, oxygen, equipment, fuel, scientific instruments. A return vehicle. You can't leave astronauts on Mars. You need to get them back. Contingency plans. What if the launch window is missed? What if something breaks during the mission? You need backup systems and decision points. The first Mars missions will probably be government funded. NASA, ESA, Russia, China, or international partnerships. But SpaceX's Starship is designed with an interesting vision: fully reusable rockets that can refuel in space and make multiple trips. This could eventually reduce the cost of reaching Mars from hundreds of billions to tens of billions. Eventually, if costs drop enough, private companies and even entrepreneurs might plan Mars missions. But Mars is not the final destination for human space exploration. The Moon and Mars are within our solar system. Beyond them lie the giant planets: Jupiter, Saturn, Uranus, Neptune. Jupiter is 5 times farther from the Sun than Mars. At its closest, Jupiter is 550 million kilometers away. A crewed mission to Jupiter would take years to reach. Jupiter is massive, 11 times wider than Earth. It has 95 known moons, including the 4 large Galilean moons: Io, Europa, Ganymede, and Callisto. Europa interests astrobiologists because it has a subsurface ocean potentially containing more water than Earth's oceans. That ocean might harbor life. But visiting Jupiter presents challenges. The planet has intense radiation belts that would be lethal to astronauts. The extreme distance means communication delays. Light takes 40+ minutes to travel from Earth to Jupiter. Astronauts would need to be incredibly self-sufficient. A human mission to Jupiter's moons might happen in the late 2010s, or later, once we've developed better propulsion technology and life support systems. Saturn is even farther, nearly twice Jupiter's distance. Titan, Saturn's largest moon, has a thick atmosphere and liquid methane lakes. Scientists consider it a potential destination for future research. Uranus and Neptune are even more remote. A mission to Neptune would take many years, even with advanced propulsion. These missions represent the frontier of human space exploration within our solar system. They're feasible in principle, but require technology more advanced than what we have today. The real frontier lies beyond the solar system. Other stars are incomprehensibly far away. Alpha Centauri, the nearest star system, is 4.37 light-years away. Light takes 4.37 years to travel from Alpha Centauri to Earth. A spacecraft traveling at the speed of Apollo, 40,000 kilometers per hour, would take 110,000 years to reach Alpha Centauri. Think about that. Modern civilization is only 5,000 years old. To reach the nearest star at Apollo speeds would take 22 times longer than recorded human history. Even at 10% the speed of light, which would require revolutionary propulsion technology, a journey to Alpha Centauri would take 44 years. The fundamental problem is energy. Accelerating a spacecraft to significant fractions of light speed requires energy on a scale that's almost incomprehensible. Let me illustrate with a thought experiment. A spacecraft carrying 10 people and supplies for a journey to Alpha Centauri might weigh 1,000 tons. To accelerate this spacecraft to 10% light speed requires energy equal to about 500 billion megawatt hours. That's equivalent to the total energy consumption of the United States for several years. And that's just the kinetic energy for acceleration. You'd also need to decelerate when you arrive, another 500 billion megawatt hours. Propulsion technologies proposed for interstellar travel include antimatter engines. Antimatter-matter annihilation releases more energy than any chemical reaction, but producing antimatter requires enormous energy, and storing it safely is nearly impossible. Fusion propulsion. Instead of chemical rockets, use controlled nuclear fusion to heat propellant. This would be far more efficient than chemical rockets, but still limited in what velocities it can achieve. Ion drives electrically accelerate ions to very high velocities. Several ion drives currently operate in space, but scaling them up for crewed missions is challenging. Solar sails use massive mirrors to catch photons from the sun or a laser. The radiation pressure pushes the sail. Without fuel to carry, solar sails could achieve very high velocities over time, but they work better closer to the sun and wouldn't work once you're far from any star. Warp drives, theoretical concepts that might allow faster than light travel by distorting space-time, but they require exotic matter and negative energy densities that might not exist or might be impossible to contain. They're mostly science fiction. Generation ships, massive spacecraft designed to support human populations for hundreds or thousands of years. Thousands of people would live their entire lives aboard the ship, and their descendants would eventually arrive at the destination. The generation ship concept is interesting because it doesn't require breakthrough technology. It requires scale and sustained funding. A generation ship might be a hollowed out asteroid with rotating sections to create artificial gravity. Hydroponics would provide food. Closed loop life support would recycle air and water. The challenge isn't technological, it's biological and social. Could humans actually live aboard a generation ship for centuries? Would they maintain the mission when their ancestors lived and died for nothing they would ever see? Interstellar travel raises profound questions about human motivation and persistence. Assuming we somehow reached Alpha Centauri, after 44 years of travel, what would we find? The system has 3 stars. The largest, Alpha Centauri A, is similar to our Sun. Proxima Centauri, the closest, is a red dwarf. Proxima Centauri has been confirmed to have at least 2 exoplanets. One, Proxima Centauri b, is roughly Earth-sized and in the habitable zone, but we don't know if Proxima b has an atmosphere or liquid water. It might be habitable in principle, but a barren rock in practice. Even if we found a habitable world at Alpha Centauri, we'd face new challenges. Establishing a human settlement would require bringing equipment, supplies, and seeds to grow Earth plants. The alien ecosystem, if one exists, might be toxic to humans. Colonizing another star system would be an epic undertaking across multiple human generations. Yet if humans are to survive long term, eventually we need to establish settlements beyond Earth. Earth faces existential risks: asteroid impacts, supervolcanic eruptions, nuclear war, climate change, engineered pathogens, artificial intelligence risks, and others. No single risk is certain to cause human extinction, but collectively, the probability of civilization-ending catastrophe increases over time. One solution is spreading humans across multiple planets and eventually multiple star systems. If humanity exists on thousands of worlds, no single catastrophe can extinguish us. This is the long-term vision that motivates some space exploration, creating a spacefaring civilization that eventually reaches other stars. But this vision is centuries or millennia away. The nearer-term future, the next century, focuses on the inner solar system. Mars will be humanity's first true colony. After establishing settlements on Mars, Humans will likely explore the moons of Jupiter and Saturn. Bases on the Jovian and Saturnian moons would require advanced technology. The distances are enormous, radiation intense, and life support systems must work for years. But these moons have resources. Water ice can provide drinking water and fuel. Minerals in the regolith can be mined. Some moons have subsurface oceans, potentially containing resources and microbial life. Mining the asteroids for precious metals and water is another possibility. Automated spacecraft could already be mining asteroids within decades. Human miners might follow. The outer solar system, Uranus, Neptune, and the Kuiper Belt are the frontier beyond that. Permanent settlements there are probably 200 plus years away. Beyond the solar system, the timescales extend to centuries or millennia. But here's something to consider. We don't need to rely on chemical rockets forever. One day, perhaps in the next century, humans might develop nuclear fusion propulsion. If we could achieve 1% the speed of light, a fraction of what fusion theoretically allows, reaching other stars becomes possible in human lifespans. At 1% light speed, Alpha Centauri is 437 years away. Still a long time, but less than the age of nations. A spacecraft could carry a small population that lives aboard for 400 plus years, arriving in the star system with generations still alive who remember the journey. This is the vision scientists like Tau Zero Foundation propose, using advanced propulsion to enable interstellar travel within decades or centuries rather than millennia. The technical challenges are enormous, but the physics doesn't forbid it. Now, what about traveling to other galaxies? This is where we encounter the truly cosmic scale. Andromeda, the nearest large galaxy, is 2.5 million light years away. Light from Andromeda takes 2.5 million years to reach Earth. At 1% light speed, reaching Andromeda would take 250 million years. The age of the solar system is 4.6 billion years. Reaching Andromeda would take 5% of that time. But more importantly, it would take roughly 250 times longer than humans have existed as a species. To reach Andromeda, humanity would need to maintain a civilization and space program for 250 million years. That's so long that evolutionary change would turn us into something entirely different. Traveling to other galaxies is so far in the future, if possible at all, that it's mostly philosophical speculation. The universe has roughly 200 billion galaxies. Some are millions of light years away. The Virgo supercluster alone spans 110 million light years. At our current understanding of physics, crossing such distances is impossible. Relativity forbids faster than light travel. Time dilation means that traveling at relativistic speeds feels like brief journeys to the traveler, but takes enormous time in the outside universe. But physics is not completely understood. Maybe undiscovered physics permits faster than light travel. Maybe one day we'll harness energy sources we haven't discovered. Maybe there are solutions we simply haven't thought of. From our current perspective in 2026, interstellar travel seems barely possible, and intergalactic travel seems impossible. But consider, in 1900, powered flight was impossible. People thought airplanes violated physical law. Yet within a decade, planes flew. Within a century, we landed on the moon. Technologies that seem impossible often become inevitable once someone figures out how. Maybe in 500 years, spacecraft travel at relativistic speeds routinely. Maybe in 5,000 years, reaching other galaxies is feasible. Maybe in 1,000,000 years, humans explore galaxies across the observable universe. Or maybe not. Maybe the speed of light is an absolute limit we never overcome. Maybe interstellar travel remains eternally difficult and rare. We can't know, but we can imagine. Let me paint a picture of what human space exploration might look like across different timescales. In the next 50 years, roughly to 2075, humans establish a permanent base on the moon, with rotating crews of astronauts spending months or years there. Humans land on Mars, initially in brief missions. Later, permanent settlements are established. Mars is inhabited by thousands of people living in habitats, mining water ice, conducting research. Automated spacecraft explore the rest of the solar system. The first spacecraft to return samples from asteroids are launched. Private space companies operate regular transportation between Earth, the Moon, and Mars. Space tourism is possible for the wealthy. Fusion rocket engines are tested. The first spacecraft with advanced propulsion systems are launched, achieving speeds significantly higher than chemical rockets. In the next 200 years to roughly 2025, humans are born on Mars who have never seen Earth. Second-generation Martians grow up knowing only the red planet. Bases exist on moons of Jupiter and Saturn. Ice mining is underway. Scientists search for life in subsurface oceans. Asteroid mining is extensive. Billions of tons of material are extracted annually. Rare metals and water ice are shipped to human settlements throughout the solar system. The first spacecraft designed for interstellar travel is launched. It's crewed by volunteers who know they're part of a journey that will take generations to complete. Robotic probes have visited every planet and explored the outer reaches of the solar system. In the next 1,000 years to 3025, the first interstellar colony has been established around a nearby star. It took 400 to 500 years to get there, but humans are now living and working in another star system. Multiple human settlements exist throughout the solar system. Mars is inhabited by millions. Cities exist on the moons of Jupiter and Saturn. Advanced propulsion technology has enabled faster travel. New spacecraft reach Alpha Centauri in 50 years instead of 400. Robotics and artificial intelligence have become incredibly advanced. Most exploration is conducted by machines, with human colonies established only where humans want to live. The solar system is extensively mapped and explored. Resource extraction is a major industry. Humans in the outer solar system enjoy lives very different from those on Earth or Mars. Beyond 1,000 years, prediction becomes pure speculation. Technology evolves in unpredictable ways. Civilizations rise and fall. Wars happen. Scientific breakthroughs occur that change everything. But if humanity survives and persists in exploring space, the trajectory is clear. Outward from Earth, across the solar system, to nearby stars, and eventually across the galaxy. This is the long-term future of human space exploration. But let's return to the near term, the next few decades, because that's where we can actually make plans. Getting humans to Mars is the immediate frontier. The challenges are less about physics than about engineering, politics, and funding. Technically, we know how to send humans to Mars. The spacecraft don't exist yet, but the designs are credible. Propulsion, life support, radiation shielding, landing systems, all are engineering problems we're confident we can solve. The political challenge is gaining support from government officials and taxpayers who have competing priorities. Climate change, healthcare, education, poverty. These are urgent problems demanding resources. Space exploration seems like a luxury, but history suggests that investing in space exploration has broad benefits. Technologies developed for space, water purification, life support systems, advanced materials, medical devices often find applications on Earth. The Apollo program contributed technologies used in medicine, transportation, and industry. The economic challenge is cost. A program to establish humans on Mars might cost hundreds of billions of dollars spread over multiple decades. But this is manageable. US government spending is trillions of dollars annually. A Mars program costing $100 to $200 billion over 20 years is roughly 1% of government spending. Significant, but not impossible. Private companies might accelerate this timeline. SpaceX's goal is to make Mars accessible within decades. If SpaceX's Starship reaches operational status, it could reduce the cost of Mars missions by orders of magnitude. Other countries are also investing. China has an ambitious space program and is working toward Mars exploration. The European Space Agency, Russia, India, Japan, and others are developing advanced spacecraft. The competition might actually accelerate progress. If multiple organizations are working toward Mars, the combined effort moves faster than any single organization could. So it's plausible that humans reach Mars within your lifetime. If you're young, you might see humans walking on Mars before you're old. What would a Mars settlement look like? Early bases would be small, perhaps a dozen people, housed in pressurized habitats. These habitats would be constructed before humans arrive, delivered by automated spacecraft. The base would have sleeping and living quarters for the crew, life support systems recycling air and water, laboratories for conducting science, equipment for mining water ice and extracting oxygen from the Martian soil, power systems, likely solar panels and possibly nuclear reactors, communication systems maintaining contact with Earth, medical facilities, though limited compared to Earth hospitals, food production systems, hydroponics, and possibly greenhouses. As the settlement grows, more habitats are added. Eventually, you'd have a small town with hundreds or thousands of people. The first settlements would be near the poles, where water ice is accessible. Later settlements might spread to other locations as technology improves. Eventually, this is centuries in the future, Mars might have a self-sustaining civilization. Humans born on Mars would outnumber immigrants from Earth. Mars would be home rather than a frontier post. At that point, Mars becomes not just a scientific outpost, but a world. This is the vision that excites space enthusiasts. A second home for humanity, a planet where humans live, work, raise families, build cultures, where generations grow up learning Martian geology and soil science alongside history and literature. Whether this dream becomes reality depends on choices humanity makes in the coming decades. We could choose to prioritize Mars exploration and funding. If governments and corporations commit resources, humans could establish settlements on Mars within 20 years and expand them over the next century. Or we could choose other priorities. Solving climate change, addressing poverty, developing new energy sources, all are crucial and worthy of investment. Ideally, we'd pursue all of these simultaneously, but resources are finite and choices have consequences. One perspective is that space exploration is insurance. By establishing humans on multiple worlds, we ensure humanity's survival even if catastrophe strikes Earth. Another perspective is that space exploration is inspiration. Reaching Mars unites humanity around a common goal, demonstrating what we're capable of, inspiring new generations to pursue science and engineering. A third perspective is that space exploration is inevitable. Humans are explorers by nature. We've explored every continent, every ocean, the skies. Space is the next frontier. We'll explore it whether governments fund it or not. All three perspectives contain truth. For now, let's focus on what's happening. NASA is building the Space Launch System, a massive rocket designed to launch spacecraft to the moon and beyond. The first crewed Artemis mission to the moon is expected in 2025, pending schedule delays. SpaceX is testing Starship, a fully reusable spacecraft designed for Moon, Mars, and potentially interstellar missions. Starship has already completed multiple test flights. Full operational capability is targeted for the mid-2020s. The European Space Agency and international partners are developing complementary systems. Russia is pursuing its own space program despite international tensions. China has an ambitious timeline for moon exploration and plans for Mars missions. Private companies including Blue Origin, Axiom Space, and others are developing lunar landers, spacecraft, and habitats. The convergence of these programs suggests that this decade is a turning point for human space exploration. By 2035, humans will likely be living on the moon long term. By 2045, humans will likely have landed on Mars and established the first base. By 2065, Mars might have permanent settlements with hundreds of people. This is decades away, but within reach of current technology and efforts. The challenge isn't, can we do it? But will we do it? The answer depends on sustained commitment and funding. Now let's consider the human side of space exploration. Traveling to Mars means months in a confined spacecraft. Astronauts will experience microgravity for 8 months, muscles atrophy, bones lose calcium. The body adapts to the absence of gravity in ways we're only beginning to understand. Radiation exposure exceeding safe limits, increasing cancer risk, and potentially causing cognitive effects. Isolation from Earth and everyone they know except their crewmates. Danger. Space travel is inherently risky. Systems fail. Emergencies happen. A medical crisis during the journey has limited options for treatment. Psychological challenges. 8 months in a small spacecraft with the same few people is psychologically taxing. Astronauts must be carefully selected and trained. Yet humans persist in facing these challenges because exploration is central to human nature. The astronauts who walk on Mars will be among the most accomplished humans alive. Their training will exceed anything previously attempted. Their courage will be extraordinary, and they'll face a planet that's hostile to human life in ways that make the journey to Mars seem simple. Mars has 1/3 of Earth's surface gravity. Humans living in 1/3 gravity will experience constant stress on their bones, muscles, and cardiovascular system. Over time, people adapted to Earth gravity might suffer permanent changes in Mars gravity. Mars has no magnetic field. Cosmic radiation reaches the surface at levels dangerous to humans. Long-term exposure increases cancer risk and potentially causes neurological damage. Mars's atmosphere is 95% carbon dioxide with an atmospheric pressure less than 1% of Earth's. Humans can't breathe the Martian air. They need spacesuits to go outside. Temperatures on Mars range from -60 degrees Celsius at night to perhaps 20 degrees Celsius at the equator on a sunny day. The average is about -65 degrees Celsius. Humans can survive this with proper equipment, but they can't easily venture outside. Dust is pervasive. Martian dust is electrostatically charged and abrasive. It damages equipment and gets into machinery. It contaminates habitats. The Martian day is 24 hours 39 minutes, close to Earth's 24 hours, but not exactly. Humans will adapt to a slightly different circadian rhythm. Despite these challenges, humans will adapt. Just as humans adapted to living at sea level and in high mountains, in deserts and Arctic regions, humans will adapt to Mars. The first generations will probably spend their entire lives in habitats, but as technology improves, they might venture outside in less restrictive suits. Eventually, perhaps genetic engineering or technological enhancement might allow humans to tolerate Martian conditions. But that's centuries in the future. The near-term reality is that Mars colonists will live confined, difficult lives in an alien world. They'll do it because they're explorers and because they want to be part of humanity's expansion into space. What drives humans to do this? Some are motivated by science. Mars holds answers to questions about planetary evolution, the nature of life in Earth's future. Scientists want to study Mars directly rather than through remote instruments. Some are motivated by history. Walking on Mars means being part of an event that will be remembered for centuries. It's a form of immortality, your name attached to an incredible achievement. Some are motivated by wonder, looking up at Mars in the night sky, visible to the naked eye, and knowing that humans will live there, build cities, create cultures. This inspires awe. Some are motivated by competition. Nations want to demonstrate technological prowess. Being first on Mars confers prestige and geopolitical advantage. Some are motivated by survival. They believe humanity must become a space-faring civilization to ensure our long-term survival. All of these motivations are valid. All have played roles in driving space exploration throughout history. The Apollo program succeeded because it combined multiple motivations. Science wanted to study the moon. Presidents wanted to win the space race. Engineers wanted to solve the problems. The public wanted to see humans achieve the impossible. A similar convergence of motivations is driving current efforts to reach Mars. Now let's talk about the actual physics of long-distance space travel. When you want to travel from one world to another, you can't just point your spacecraft and fire the engines. That would waste enormous amounts of fuel. Instead, you use orbital mechanics. Earth orbits the Sun in a roughly circular path. Mars also orbits the Sun, but at a larger radius and taking longer. To go from Earth to Mars, you put your spacecraft into an elliptical orbit that touches Earth's orbit at one end and Mars's orbit at the other. This is called a Hohmann transfer orbit. You time your departure so that you launch when Mars is in the right position. When you arrive at Mars's orbit, Mars is there waiting. This is efficient in terms of fuel, but it requires waiting for launch windows. Earth and Mars are only in favorable positions for transfer every 26 months. If you miss a launch window, you wait. This is why Mars missions are infrequent. You can't send a spacecraft whenever you want. You have to wait for the planets to align. Once you reach Mars, you can't just land on the surface. You need to decelerate. You enter Mars's orbit, then gradually reduce your altitude until you're in a position to land. Landing on Mars is a major challenge. Mars has enough atmosphere to cause drag, while slowing down landing spacecraft. But Mars's atmosphere is too thin to use parachutes effectively. Most Mars landers use a combination of heat shields, parachutes, and retrorockets to slow down. It's a complex dance of deceleration. The Apollo lunar module used retrorockets to land slowly on the Moon, which has no atmosphere. Mars is trickier because of the thin atmosphere. Future Mars landers might use more advanced techniques. SpaceX's Starship is designed to use retrorockets for landing, similar to the Apollo module, but on a much larger scale. The return trip from Mars is even more complex. You need to launch from Mars, rendezvous with an orbiting spacecraft, and then execute a return trajectory to Earth. All of this has to work perfectly. A failure at any stage means the mission fails, potentially with loss of life. This is why Mars missions have extensive redundancy and backup systems. Every critical function has backup systems. Decisions are made conservatively, prioritizing crew safety. It's also why the first Mars missions will be government-funded. Only government agencies have the resources and risk tolerance for such ambitious missions. Private companies will eventually join, but not until the risks are better understood and costs are reduced. The economics of space travel are changing. SpaceX demonstrated that fully reusable rockets are feasible. The Falcon 9 rocket lands its first stage and returns it to flight, dramatically reducing per-flight costs. Starship will be fully reusable, both booster and spacecraft. This could reduce the cost of reaching Mars by a factor of 10 or more compared to expendable rockets. Lower costs make frequent missions possible. Eventually, regular supply missions to Mars could operate like airline flights operate on Earth. Not cheap, but routine. At low flight costs, private companies can operate in space profitably. Space tourism could happen. Space mining becomes economically viable. This economic transformation is the key to making space accessible. Currently, reaching space costs roughly $1,000 per kilogram to reach low Earth orbit. SpaceX's stated goal is to reduce this to $10 per kilogram through Starship. At $10 per kilogram, it becomes affordable to send large quantities of supplies, equipment, and eventually people to space regularly. This is the vision behind Starship and other reusable vehicles, making space accessible economically. If this succeeds, space exploration accelerates dramatically. Missions that are currently impossible become routine. Let me project forward to a scenario where space is accessible. By 2050, let's imagine that SpaceX Starship or similar vehicles have achieved low launch costs. Space transportation is routine. Earth-to-orbit costs are a few $100s per kilogram. At these costs, establishing a moon base is economically feasible. Supplies are shipped regularly. Hundreds of people live and work on the moon. Mars missions launch regularly. Every 26 months, when the launch window opens, multiple spacecraft head to Mars. A spacecraft might be fully reusable, making many trips. Mars settlements have grown to include thousands of people. Mining operations are extracting water ice and metals. Laboratories are conducting research. Factories are producing equipment for use on Mars. Space hotels orbit Earth and the Moon, catering to wealthy tourists. Resource extraction companies operate asteroid mining missions. Asteroids rich in water and metals are being processed. Materials are shipped to space settlements. The Moon serves as a hub for supply transfer. Spacecraft from Earth dock at the Moon, transfer cargo to spacecraft, heading deeper into the solar system and return to Earth. This is the scenario if technological progress accelerates and funding continues. Alternatively, progress could stall. Budget cuts, technological setbacks, loss of public interest, any of these could slow or stop space exploration. The outcome is not determined. It depends on choices humanity makes. But assuming progress continues, this is a plausible future. Going deeper, consider the next century. By 2125, humans might be living throughout the inner solar system. The Moon has cities. Mars has a self-sustaining civilization. The moons of Jupiter are being explored and settled. Spacecraft are traveling between worlds regularly. A journey to the outer solar system takes years, but it's routine for specialized crews. Advanced propulsion, possibly fusion-based, enables faster travel. Reaching the moons of Jupiter takes months instead of years. Mining and resource extraction are major industries. Water from asteroids and icy moons is processed. Metals are refined and shipped to settlements. Science is advancing rapidly. With bases throughout the solar system, scientists study planetary geology, astrobiology, physics, and astronomy in ways impossible from Earth. The first human children born on Mars or the outer planets are growing up. They're adapted to local gravity and radiation. They're culturally distinct from Earth-born humans. Languages might diverge. Children born on Mars in isolation might develop accents or vocabulary adapted to their environment. Political systems might diverge. Mars colonies might develop independent governance, distinct from Earth-based nations. This is the scenario for the year 2125 if progress continues. By 2225, 2 centuries from now, the picture becomes more speculative. Humans might be living on moons throughout the solar system, permanent settlements on Europa, below the ice, Enceladus, Titan, and others. The first interstellar spacecraft might be approaching Alpha Centauri. It launched in 2150 with a crew that's now 3 or 4 generations down. Earth has received communications, but no one who launched is alive. Space-based industry is enormous. Trillions of dollars of economic activity occurs in space annually. More people live in space than on Earth. This last part is probably too optimistic, but it's a scenario to consider. Technology has advanced beyond our understanding. Artificial intelligence, genetic engineering, nanotechnology, applications of these could transform human civilization. Earth has stabilized. Climate change is managed. Population is stable or declining. Earth is treated as a precious heritage world, largely preserved in natural state. Humans are truly a spacefaring civilization, living and working throughout the solar system and beginning to reach beyond it. This is fantasy territory, pure speculation. But it's speculation grounded in the physics we understand in extrapolating current technological trends. What about reaching other galaxies? At this point, we're in deep science fiction territory. Andromeda is 2.5 million light-years away. Even traveling at 1% light speed, a technological miracle, takes 250 million years. To reach Andromeda would require technology far beyond anything we can currently imagine. A civilization that persists for millions of years without collapse, stagnation, or fundamental change in values. Spacecraft capable of lasting millions of years, or ways to build new spacecraft mid-journey. Ways to sustain human populations across such vast timescales. The last point is crucial. Humans age and die. A 250 million year journey would see uncountable generations born and die aboard spacecraft. Would they maintain the mission? Would they stay committed to reaching a destination that ancestors set out for and that descendants might never see? History suggests it's difficult to maintain focus across centuries. Cultures change, priorities shift, civilizations rise and fall. Maintaining a space program across millions of years seems impossible. Unless civilization achieves extreme stability, something like an eternal society that values exploration above all else. Or unless technology advances to radical longevity or digitization. If humans could upload their minds to computers and exist as digital beings, a 250 million year journey becomes feasible. You'd experience the journey as subjective time, sleep between stars, Wake at Andromeda. This is the realm of extremely advanced science fiction. We don't know if it's possible, but if civilization ever reaches the technological capability, interstellar travel is more feasible than intergalactic travel. Intergalactic travel remains in the realm of pure speculation. We can imagine it, but can't seriously plan for it. The realistic frontier for human space exploration is the solar system. The next few centuries and nearby stars beyond that, travel to other galaxies remains beyond even optimistic technological projections. But the universe is vast and old. Maybe civilizations older than humanity have solved this problem. Maybe some civilization millions of years old routinely travels between galaxies. That's speculation beyond our current understanding. For now, Mars is the frontier. After Mars, the moons of Jupiter and Saturn. After that, nearby stars. The rest of the galaxy beyond that, if technology permits. The timeline is centuries or millennia, but it's a direction. Outward, forever outward. This is the vision that drives space exploration. Humans reaching further, exploring deeper, and eventually spreading throughout the cosmos. It might be naive, it might be impossible, or it might be the ultimate achievement of human civilization. We're at the beginning of this story. The first chapters are being written now. The astronauts who walk on Mars in the coming decades will be early characters in this vast narrative. Let me discuss the history of human spaceflight more deeply, because it informs where we're going. The space age began in 1957 when the Soviet Union launched Sputnik 1, a simple satellite that orbited Earth and transmitted radio signals. This event shocked the world. The Soviets had beaten the Americans to space. Suddenly, the idea of humans in space seemed imminent. In 1961, Soviet cosmonaut Yuri Gagarin became the first human in space, orbiting Earth once in the Vostok spacecraft. Americans responded with Project Mercury, putting the first American, Alan Shepard, into suborbital flight in May 1961. The space race was on. Both superpowers wanted to demonstrate technological superiority. Both invested enormous resources in spaceflight. Americans shifted to Project Gemini, which developed spacecraft for 2 astronauts and techniques for rendezvous and docking in orbit. Then came Project Apollo, President Kennedy's bold commitment to land humans on the moon before 1970. On July 20th, 1969, Apollo 11 landed on the moon. Neil Armstrong and Buzz Aldrin walked on the lunar surface while Michael Collins orbited above. Watching the Apollo missions, people believed space exploration would accelerate. Surely humans would establish bases on the moon, go to Mars, eventually explore the solar system. But it didn't happen that way. After Apollo, momentum stalled. The space race's urgency faded. No new president championed an ambitious space program. Funding was redirected to other priorities. The last humans visited the moon in 1972. For over 50 years, no human has returned. The Space Shuttle program maintained spaceflight capability, but focused on low Earth orbit, not deep space exploration. Now, in the 2020s, we're resurrecting the vision of returning to the moon and going to Mars. Why did momentum stall? Several reasons. Cost. Apollo required roughly $100+ billion in modern dollars annually at its peak. That's expensive even for superpowers. Loss of urgency. Once the Soviets lost the space race, American government interest declined. Disasters. The Apollo 13 oxygen tank explosion shook confidence. The Space Shuttle Challenger and Columbia disasters in 1986 and 2003 killed crews and setback programs by years. Changing priorities. Other issues demanded government attention and funding. Lack of commercial value. The moon doesn't have resources to extract profitably with 1970s technology. Mars had no economic incentive to explore. But things have changed. Technology has advanced. Costs are dropping. Commercial interest is increasing. Multiple countries are pursuing space exploration. The time is right for expansion into the solar system. Now let me discuss the specific challenges of human space travel in detail. Radiation is one of the biggest challenges. In space, beyond Earth's magnetic field, cosmic rays bombard everything. Earth's magnetic field deflects most cosmic rays. It's like a protective bubble around our planet. But in space, humans are exposed. The radiation dose increases rapidly with altitude and distance from Earth. On a journey to Mars, an astronaut receives a radiation dose of roughly 300 to 1,000 millisieverts, depending on the spacecraft shielding. For comparison, the US yearly occupational limit for radiation workers is 50 millisieverts. The dose on a Mars journey is 6 to 20 times this. This level of radiation increases cancer risk. It might also cause acute radiation sickness, damage to the nervous system, cataracts, and other health problems. Shielding helps. Placing heavier materials between astronauts and space reduces radiation. But complete shielding is impossible. Radiation would penetrate any reasonable shield. Timing also matters. The sun produces solar radiation events where intense particles are ejected. Astronauts need to shelter in well-shielded areas during these events. Long-term, one solution is developing radiation-resistant biology. Genetic engineering might make humans more tolerant of radiation, or pharmaceutical countermeasures might reduce radiation damage. But for near-term Mars missions, astronauts will accept elevated radiation risk as part of the mission. Microgravity is another challenge. Humans evolved in one-gravity environments. Our bodies adapted over millions of years. In microgravity, muscles atrophy because they're not fighting against gravity to hold you up. Bones lose calcium. Without load bearing, bones lose density at about 1% per month. Blood redistributes from legs to upper body. This causes facial puffiness, but also reduces return blood flow to the heart. The inner ear, which senses balance, gets confused. Most astronauts experience space sickness for a few days. Eyes change. Microgravity increases intracranial pressure, flattening the eyeball and affecting vision. The immune system is impaired. Some immune functions decrease in space. Astronauts mitigate these effects through exercise. On the International Space Station, astronauts spend 2+ hours daily on exercise equipment, fighting microgravity effects. But for months-long journeys to Mars, the effects accumulate. When astronauts arrive on Mars and experience 1/3 gravity, their deconditioned bodies must adapt to a new gravity environment. Long-term, humans might adapt to Martian gravity. Children born on Mars would develop in 1/3 gravity and might be permanently adapted to it. But moving between gravity environments, Earth to space to Mars, is challenging physiologically. Another challenge is psychological. 8 months in a spacecraft with 5 or 6 crewmates, no privacy, limited communication with Earth, there's a 20-minute communication delay, and the knowledge that something going wrong means death. This is psychologically demanding. Astronauts are carefully selected and trained, but no training can fully prepare you for months of confinement and danger. Historical records from exploration expeditions, polar explorers, submarine crews, Antarctic researchers show that long isolation can cause depression, conflict, reduced motivation, and psychiatric issues. The first Mars missions will carefully monitor crew psychology. Detailed records of what works will inform future missions. Another challenge is medical emergencies. What happens if an astronaut gets sick during the journey? On the International Space Station, which orbits Earth, help is available. A spacecraft can launch to rescue astronauts in emergency. But in transit to Mars, you're on your own. A medical emergency during the journey means improvising with limited resources. The spacecraft will have a medical kit, but nothing compared to Earth hospitals. Surgeries would be difficult without proper operating rooms. Medications might be limited. Anesthesia might be risky in microgravity. The safest approach is prevention. Select astronauts in peak health. Screen for potential problems. Keep the crew healthy during the mission. But emergencies happen unpredictably. Early Mars missions will probably have redundancy in crew. If one person becomes incapacitated, others can take over their responsibilities. Later missions might include medical specialists, actual physicians as crew members. Another challenge is reliable systems. Every piece of equipment on a Mars spacecraft must work reliably for over a year. A computer might crash, requiring reboot. A communication system might fail, requiring repair. A water recycler might break, requiring fixes. But the spacecraft will have limited spare parts. You can't exactly call a repair shop when you're 200 million kilometers from Earth. The solution is extensive testing, redundancy, and designing systems that are repairable by astronauts who aren't specialists. Every critical system has backups. Communications has multiple antennas and transmitters. Life support has redundant components. The spacecraft design emphasizes reliability. Systems are simple when possible. Complex systems are tested extensively before flight. Astronauts train on repairs. They practice fixing systems in simulations. They carry spare parts and repair tools. But despite precautions, failures might happen. Part of being an astronaut is accepting risk and being prepared to improvise. Another challenge is daily life operations. Eating, sleeping, hygiene, waste management. These are different in space. Food is specially prepared, either freeze-dried or thermostabilized, heated and sealed. It doesn't taste like Earth food, but is nutritious. Astronauts float while eating. They have to be careful not to spill food or water. Floating crumbs would contaminate the spacecraft's equipment. Sleeping in microgravity requires sleeping bags to prevent you from floating around during sleep. Hygiene is challenging. You can't take a shower in microgravity. Water would float. Astronauts use wet wipes for bathing. Toilets are sophisticated systems that use airflow to manage waste. They're uncomfortable compared to Earth toilets, but functional. These daily life challenges accumulate. Living months in uncomfortable conditions requires psychological resilience. But humans adapt. Astronauts have spent months on the International Space Station and adapted to these conditions. The same resilience would apply to Mars journeys. Now let me discuss the economy of space travel more deeply. Currently, launching to low Earth orbit costs roughly $1,000 to $2,000 per kilogram with expendable rockets. SpaceX's Falcon 9 reusable first stage reduces this to perhaps $1,000 to $1,500 per kilogram. Starship is targeting $10 per kilogram for fully reusable operation. At $1,000 per kilogram, launching a 1-ton payload costs $1 million. Launching a 100-ton spacecraft to orbit costs $100 million. This is expensive, limiting who can afford spaceflight. At $10 per kilogram, a 100-ton spacecraft costs $1 million to launch. Suddenly, much larger activities become affordable. This cost reduction is transformative. With $10 per kilogram launch costs, private space stations become affordable. Axiom Space is already planning a commercial space station at higher launch costs. At $10 per kilogram costs, many more competitors enter the market. Space tourism expands. Currently, it costs $100,000 plus per person for a brief suborbital flight. At lower costs, orbital vacations become more accessible. Asteroid mining becomes economically viable. Asteroids contain water, metals, and minerals. With high launch costs, mining isn't profitable. With low launch costs, shipping extracted materials to space settlements becomes profitable. Manufacturing in space becomes feasible. Some materials, pharmaceuticals, and electronics might be manufactured more efficiently in microgravity. With low launch costs, space-based industry becomes viable. This economic transformation could be as important as the technological capabilities. SpaceX is betting its future on Starship achieving low-cost reusable launches. If they succeed, space economy accelerates dramatically. Other companies are developing competing systems. Relativity Space is testing 3D printed rockets. Axiom Space is developing space stations. Blue Origin is developing lunar landers and space tourism. The competition is driving rapid innovation. Now let me discuss international cooperation in space. Space exploration increasingly involves multiple countries. The International Space Station is a joint project of NASA, ESA, Roscosmos, JAXA, and other agencies. Despite geopolitical tensions, nations cooperate on the ISS. It's an example of peaceful international collaboration. Future Mars missions will likely involve international partnerships. A single nation couldn't afford an ambitious Mars program alone. Combining resources from multiple countries makes missions feasible. The Artemis Accords, formulated by multiple countries, establish principles for space exploration. They include commitments to transparency, peaceful use of space, and sharing scientific results. Over 40 countries have signed the accords, suggesting broad international commitment to space exploration. This cooperation is important. Space exploration benefits from diverse perspectives and combined resources. But geopolitical tensions could complicate cooperation. If major powers go to war, space cooperation becomes difficult. The question is whether space exploration can remain a domain of peaceful international collaboration despite terrestrial conflicts. History suggests it's possible. The Cold War raged while space cooperation proceeded. The moon race was competition, but it didn't escalate to military conflict in space. Hopefully, space remains a domain of scientific exploration and cooperation, not militarization. Now let me discuss the role of different organizations in future space exploration. NASA plans the Artemis program for moon exploration and uses this as a stepping stone to Mars. SpaceX is developing Starship for Mars exploration and other deep space missions. Elon Musk's vision is making humanity multiplanetary. Blue Origin is developing Blue Moon lunar lander and working toward Mars eventually. The European Space Agency is contributing with launchers and spacecraft. Russia, Roscosmos, has plans for Moon and Mars missions, though geopolitical tensions complicate cooperation. China has an ambitious space program and plans Moon and Mars exploration. India's space agency has achieved Mars orbiter missions. They're increasingly capable. Private companies like Relativity Space, Axiom Space, and others are developing technologies for space operations. Universities and international space agencies worldwide contribute research and capabilities. The convergence of these efforts accelerates progress. If any single organization can't solve a problem, another might. The competition drives innovation. Organizations want to be first to achieve milestones. The cooperation enables sharing of knowledge and resources. This combination of competition and cooperation is healthy for space exploration. Now let me address misconceptions about space travel. Misconception 1. Space travel is dangerous and we should focus on Earth problems. Reality. Spaceflight is risky, but the risks are manageable. And addressing Earth problems and pursuing space exploration aren't mutually exclusive. Governments spend trillions annually. Allocating 1% to space exploration is feasible while addressing problems on Earth. Misconception 2. Humans will live in space because Earth will become uninhabitable. Reality. Humans should establish space settlements to ensure survival and enable scientific exploration, not because Earth will become uninhabitable. Earth will remain habitable even under climate change, but becoming a multiplanetary civilization is good insurance. Misconception 3. Mars colonization will drain Earth's resources. Reality. Mars colonization requires investment, but no more than many existing government programs, and it could generate economic returns through tourism, research, and eventually resource extraction. Misconception 4. We should focus on fixing Earth before going to space. Reality. This is a false dichotomy. We can pursue both. In fact, space technology develops solutions applicable on Earth. Solar panels, water purification, materials, science all benefit from space research. Misconception 5. Space aliens will stop human space exploration, or humans will be destroyed in space. Reality. We found no evidence of nearby extraterrestrial civilizations. Humans are resilient and have adapted to every environment on Earth. Space is hostile, but not unsurvivable. These misconceptions reflect misunderstandings about space exploration's role and feasibility. The reality is more nuanced. Space exploration is challenging and expensive, but beneficial. It's not about escaping Earth, but expanding human civilization. Now let me discuss a day in the life of an astronaut on Mars. Your alarm wakes you at 6 a.m. Mars time, Martian daytime. You check your suit, the same suit you'll wear outside. In your habitat, you can breathe freely, but you're still in a pressurized enclosure. Breakfast is reconstituted food, not Earth cuisine, but nutritious and surprisingly tasty after months of spaceflight food. At 7 a.m., you check communications. Messages from Earth arrive. Family members, mission control updates, scientific data. The 20-minute communication delay means you can't have real-time conversations. You record messages that Earth receives 20 minutes later. They respond to your previous messages. At 8 a.m., you begin your daily tasks. Today, you're conducting experiments in the science lab. You're studying Martian soil, searching for microbial life or chemical signatures of past life. At 10 a.m., you take a break. Exercise is mandatory, 90 minutes daily to combat muscle atrophy. The habitat has a centrifuge or resistance equipment. You're fighting the 1/3 gravity effect. At 11:30 a.m., you prepare for an EVA, an extravehicular activity, or spacewalk. Your suit is carefully checked. Every seal, every valve, every piece of equipment must work. A suit failure outside means death. You enter the airlock, a chamber that cycles from the habitat's atmosphere to vacuum. Air pressure drops. Your suit inflates. At 1 p.m., you exit onto Mars. The landscape is alien but familiar from months of study. Rust-colored rocks stretch across a desert. Low hills rise in the distance. The sky is tan, dust in the atmosphere. The sun is smaller than from Earth. casting long shadows in the thin atmosphere. You are alone on an alien world. Only your crewmates share this place with you. You collect samples, take measurements, and photograph the area. Your crewmate, stationed inside, watches via camera and radio, ready to help if needed. At 3 p.m., you return to the habitat. The airlock cycles. Pressure returns. You remove your suit. Your suit is checked, maintained, cleaned. Every EVA stresses the suit. It needs careful maintenance. At 4 p.m., you report to mission control. You summarize the day's activities and data collected. At 5 p.m., dinner. Reconstituted food again. You're tired but satisfied. At 6 p.m., personal time. You read, exercise, or communicate with Earth. At 7 p.m., you review tomorrow's tasks and prepare for sleep. At 8 p.m., you sleep. A Martian day is 24 hours, 39 minutes, so your sleep schedule drifts slightly compared to Earth. Tomorrow, you'll repeat similar work: science, exercise, maintenance, survival. This is the reality of Mars living. Not glamorous, but meaningful. You're expanding human knowledge and presence. Weeks blur into months. Months blur into a year. Eventually, launch day arrives. You ascend from Mars, rendezvous with a spacecraft in orbit, and begin the journey home. 9 months later, you arrive at Earth. You're among the first humans to live on another world. Your experience will shape Mars exploration for decades. Now let me discuss the far future of human space exploration. If technology continues advancing and funding persists, space exploration expands exponentially over centuries. By 2300, the solar system might be inhabited. Thousands of settlements exist on the Moon, Mars, moons of Jupiter and Saturn. Asteroid mining operations throughout the system. Space-based manufacturing, energy generation, and research are major industries. The first interstellar mission to Alpha Centauri is en route, carrying thousands of frozen colonists and extensive equipment and supplies. They'll arrive in 400 years. By 2600, humanity has fully settled the solar system. Hundreds of millions of people live in space. The inner solar system is heavily developed. The first interstellar settlements are established around nearby stars. Alpha Centauri has a human colony. The next wave of interstellar missions is launching towards Sirius, Procyon, and other nearby stars. Communication networks spanning light years transmit information between settlements. Humans on Venus's floating cities, Europa's ocean settlements, and Enceladus's installations are technologically advanced civilizations distinct from Earth. By 3000, humans inhabit star systems throughout the local neighborhood. A federation or network of human settlements spans hundreds of light years. Travel between nearby stars is routine for specialized missions, though still requiring years. Earth, meanwhile, is largely preserved. It's the historical homeland, cherished and protected. By 10,000, humanity has explored the entire galaxy. Settlements exist on countless worlds. Human civilization spans 100,000 light years. Faster than light travel, if discovered, revolutionizes everything. Suddenly, the galaxy is crossing in weeks instead of years. By 1 million AD, a difficult number to even comprehend, humanity might be an interstellar civilization spanning multiple galaxies. Or civilization might have collapsed, reformed, evolved in unrecognizable directions. Or humans might be extinct, replaced by artificial intelligence or aliens. Or spacefaring might have been abandoned as pointless, with humans choosing to live locally and sustainably. The future is genuinely unknowable. These projections are wild speculation, but they illustrate the scope of possibilities if space exploration continues. The key point is that we're at the beginning. The decisions made in the next few decades, whether to invest in Mars, build reusable rockets, develop advanced propulsion, fund long-term research, will shape centuries to come. This is why space exploration matters. It's not about escaping Earth or achieving technological prowess. It's about expanding the boundaries of human civilization and exploring the cosmos. Every species that evolves intelligence faces this choice: remain on their homeworld or expand outward. Earth has been humanity's home for 300,000 years. But we're not limited to one world. If we choose to explore, we can spread across the solar system, then to nearby stars, then to the galaxy. It's a monumental undertaking requiring sustained commitment across centuries. But it's possible. Physics doesn't forbid it. Technology doesn't forbid it. Only will and resources forbid it. And those are within our control. Now let me detail specific missions that have been proposed and might happen in the coming decades. NASA's Artemis program aims to land humans on the moon in the mid-2020s, establish a lunar base by 2030, and conduct crewed Mars missions by the 2040s. This timeline is ambitious but achievable with sustained funding. The Lunar Gateway is a planned space station in lunar orbit that will serve as a hub for lunar operations. Spacecraft will dock at the gateway. Crew will transfer to lunar landers, descend to the surface, conduct operations, then return. This architecture reduces the fuel needed for each mission by using the gateway as a refueling point. SpaceX's Starship is designed to land on the Moon and Mars directly. Starship is taller than the Statue of Liberty and can carry 150 tons of payload to the surface. If Starship achieves operational status and reusability targets, it could reduce Mars mission costs by orders of magnitude. SpaceX's timeline aims for Mars missions in the early 2030s. This is ambitious, but they're aggressively pursuing it. China's space program is increasingly capable. China has successfully landed rovers on the Moon and Mars and has plans for human moon missions and permanent lunar bases by the 2030s. The European Space Agency is developing ExoMars, a rover searching for life on Mars and planning for future human missions. Russia's space program pursues Moon and Mars missions, though geopolitical tensions create uncertainty. India's ISRO has demonstrated impressive spaceflight capability with limited budgets and is pursuing Mars exploration and Moon missions. Private companies are adding capability. Blue Origin's Blue Moon lunar lander is designed to deliver cargo and crew to the Moon. Relativity Space is developing 3D printed rockets that could enable rapid production of launch vehicles. Axiom Space is building commercial space stations. This convergence creates momentum for space exploration. Competition pushes innovation while collaboration enables sharing knowledge. Now let me discuss propulsion technology in detail. Chemical rockets use combustion of hydrogen and oxygen to produce hot gas that expands through a nozzle. Specific impulse reaches around 450 seconds for the most efficient chemical propulsion. Specific impulse measures rocket efficiency. Higher means more efficient. Chemical rockets are reaching their theoretical limit. Ion drives use electric fields to accelerate ions to very high velocities, specific impulse exceeding 3,000 seconds. Ion drives are incredibly efficient but produce low thrust. They're better for deep space missions where time isn't critical. Nuclear thermal rockets heat propellant using a reactor, producing specific impulse around 900 seconds. They could reduce Mars journey time from 9 months to 6 months. But launching nuclear reactors requires safety approvals and political support. Fusion rockets use controlled nuclear fusion to produce extremely high exhaust velocities. Theoretical specific impulse exceeds 1,000 seconds. Fusion technology remains experimental. Sustained controlled fusion for propulsion is far from reality. Antimatter propulsion annihilates matter-antimatter pairs, converting all mass to energy via E equals mc squared. Theoretical efficiency is perfect. But producing and storing antimatter requires enormous energy, currently impractical. Solar sails use radiation pressure to accelerate spacecraft. No fuel needed, just reflective surface. Solar sails work best near the sun. For large crewed spacecraft, they present maneuverability challenges. For near-term Mars missions, chemical rockets remain practical. Reusable rockets reduce costs dramatically. For deep space missions, fusion or advanced ion drives might be used centuries hence. For interstellar travel, novel concepts are necessary. Now let me address whether we could terraform Mars. Terraforming modifies a planet's environment for human habitability. Mars is a candidate because it has water ice, atmosphere, and reasonable radiation compared to other planets. Terraforming would take centuries or millennia. Challenges include Mars's thin atmosphere, extreme cold, lack of magnetic field, and one-third gravity. One scenario involves releasing greenhouse gases to warm Mars and thicken atmosphere over centuries. Another uses orbital mirrors to reflect sunlight and warm the planet. A third involves asteroid impacts to add water. These scenarios take centuries. Eventually, Mars could become warmer with more atmosphere, but gravity and radiation would remain challenges. Some propose genetic engineering humans to thrive on terraformed Mars. Long-term vision is Mars becoming a second Earth, but this is centuries or millennia away. The coming century focuses on research stations and habitats. Now let me discuss extraterrestrial life and space exploration's role. Life elsewhere would be humanity's most profound scientific discovery. It would suggest life isn't unique to Earth. Candidate locations include Mars. It had liquid water and thicker atmosphere. Life might persist underground. Europa has a subsurface ocean with potential hydrothermal vents providing energy for life. Enceladus has geysers indicating subsurface ocean and hydrothermal activity. Titan has methane lakes and possible chemical energy sources. Venus's upper atmosphere has moderate temperatures and chemical energy, though extremely acidic. Human exploration will help determine if life exists elsewhere. Discovery would change humanity's philosophical understanding. Non-discovery would suggest life is rare or unique to Earth. Either result changes how we understand the universe. Now let me discuss the practical challenges of a Mars mission in concrete detail. A spacecraft launches from Earth using a heavy-lift rocket like Starship. It enters Earth orbit, performs maneuvers to achieve a Hohmann transfer orbit to Mars. This requires precise timing. Miss the launch window and you wait 26 months. The spacecraft coasts for 9 months on the transfer trajectory. Crew lives aboard, conducts experiments, maintains systems. As Mars approaches, the spacecraft must decelerate. Can't arrive at high speed. You'd zip past. The spacecraft performs a Mars orbit insertion burn, entering Mars orbit. A landing spacecraft detaches and descends through Mars's thin atmosphere using heat shield, parachute, and retro rockets. Descent is critical. Wrong speed means crash or insufficient deceleration. The craft lands near water ice or a previous base. Crew establishes survival systems, inventories supplies, checks equipment. Then research begins. Science, exploration, infrastructure building. After a planned stay, perhaps a year, crew boards the return spacecraft. Ascent vehicle launches from Mars, reaching orbit, rendezvous with the return spacecraft. Return trajectory begins. 9 more months coasting through space. Finally, Earth arrival. The capsule re-enters atmosphere. Parachutes deploy. Splashdown in ocean. The crew emerges having spent 2+ years in space and on another world. This is the scenario for crewed Mars missions. Every step involves complex engineering, careful planning, enormous risk, but it's feasible. Technology exists in principle. Making it happen requires funding, political will, and sustained commitment. Now let me discuss the economics of Mars settlements. The first crewed Mars mission cost billions. Estimates range from $100 billion to $500 billion. This is expensive but not impossible for wealthy governments or consortiums. Subsequent missions become cheaper with reused infrastructure and learned experience. Eventually, supply missions become routine. A spacecraft makes a journey, delivers supplies, returns. With reusable rockets and efficient systems, supply missions might cost hundreds of millions. Maintaining settlements of thousands requires constant resupply. Water, food, equipment, fuel, spare parts. Eventually producing supplies locally, extracting water ice, generating power, growing food, reduces dependence on Earth. A fully self-sustaining Mars settlement requires centuries, but partially self-sufficient settlements function within decades. Long-term economics favor Mars. As Earth's population and resource consumption grow, space resources become valuable. Extracting water from Mars and asteroids, mining metals, space-based manufacturing, these become economically viable at scale. Mars settlements might eventually become economically productive, exporting value to Earth or supporting space industry. For the next century, settlements are funded by governments or organizations pursuing scientific goals. As technology improves and costs drop, commercial opportunities emerge. Now let me conclude with perspective. Humans have always been explorers. We explored Africa, crossed oceans, scaled mountains, ventured to poles. Space is the next frontier. Further than any previous frontier, more challenging, more dangerous, but more rewarding. Space exploration expands human knowledge, demonstrates our capabilities, secures humanity's long-term future. The decision to explore space isn't purely utilitarian. We explore because we're driven to understand and push boundaries. That drive makes us human. In coming decades, humans will return to the moon and establish permanent presence. Humans will land on Mars and build settlements. Humans will eventually venture to Jupiter's and Saturn's moons. Far in the future, humans might reach nearby stars. This isn't guaranteed. It requires sustained effort and resources. Civilization could collapse, priorities shift, focus change elsewhere. But if we persist, this is our trajectory, outward from Earth, across the solar system, eventually to stars. It's a monumental vision. But humanity has accomplished monumental things. We developed language, agriculture, writing, technology, science, art. We built civilizations, crossed continents, split the atom, decoded life. Reaching Mars is no more impossible than any achievement. The next chapter will be written by astronauts venturing beyond Earth, by engineers building vehicles, by scientists planning missions. It will be written by governments committing resources and individuals volunteering for danger. It will be written by anyone looking at Mars in the night sky, imagining humans there. The story continues, and that's the miracle of space exploration. It connects us not just to distant worlds, but to our own humanity and our endless capacity to dream. Thanks for watching. Let me provide more detailed exploration of specific destinations in our solar system. Venus is Earth's neighbor, sometimes called Earth's evil twin. It's similar in size to Earth, but completely uninhabitable. Venus's surface temperature reaches 460 degrees Celsius. Lead melts at 327 degrees. Venus is hot enough to melt lead. The atmospheric pressure is 92 times Earth's, equivalent to 900 meters deep in Earth's ocean. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. Humans will never walk on Venus's surface. No spacesuit could withstand the conditions. But Venus's upper atmosphere is surprisingly habitable. 50 to 60 kilometers up, temperature is room temperature. Atmospheric pressure is Earth-like. Floating cities in Venus's atmosphere are theoretically possible. Balloons filled with breathable air would be less dense than Venus's carbon dioxide atmosphere, providing buoyancy. Scientists have proposed Venus cloud cities as eventual settlements. They're far future concepts, but interesting. Exploring Venus will likely be robotic. Landers are being designed to survive slightly longer than previous missions. Jupiter is the gas giant. It has no solid surface. You can't land on Jupiter, but Jupiter has moons. Io is volcanically active, the most geologically violent body in the solar system. Eruptions are constant. Europa has a subsurface ocean. Beneath an ice crust miles thick lies a liquid water ocean. Scientists believe hydrothermal vents exist on Europa's ocean floor. These vents could provide chemical energy for microbial life. Europa fascinates astrobiologists. It's a prime location for searching for extraterrestrial life. Humans won't travel to Europa for decades, but robotic missions are already planned. Jupiter's radiation belt is intense. Spacecraft must navigate carefully. Humans visiting would need heavy shielding. Ganymede is the largest moon in the solar system, larger than Mercury. It has a subsurface ocean and possibly a magnetic field. Callisto is heavily cratered, preserving a record of impacts. Saturn is less dense than water. If you could find a bathtub big enough, Saturn would float. Saturn's rings are spectacular. They're composed of billions of particles, some ice, some rock. Titan is Saturn's largest moon. It's larger than Mercury. It has a thick atmosphere and liquid methane lakes. Titan's atmosphere is nitrogen and methane. Temperature is minus 179 degrees Celsius. The surface is covered in hydrocarbons, organic molecules. Exploring Titan means searching for exotic life forms potentially based on methane rather than water. The Cassini-Huygens mission sent a lander to Titan. It transmitted data briefly, then was overwhelmed by the environment. Future Titan missions are planned. Dragonfly, a rotorcraft lander, will explore Titan in the 2030s. Enceladus is a small moon with geysers. Water erupts from the south polar region, indicating a subsurface ocean. The geysers are active. Cassini spacecraft flew through them, collecting samples of water and organic compounds. This makes Enceladus compelling for astrobiology research. Uranus is another ice giant with no solid surface. Uranus rotates on its side. Its axis of rotation is tilted 98 degrees. Uranus has moons including Ariel, Umbriel, Titania, and Oberon. Little is known about these moons. Future missions might explore them. Neptune is the farthest planet from the Sun. Triton is Neptune's largest moon. It has nitrogen geysers and is geologically active. Triton orbits backwards, retrograde, suggesting it was captured from the Kuiper Belt. The Kuiper Belt extends from Neptune's orbit to far beyond. It contains icy bodies and dwarf planets. Pluto was reclassified as a dwarf planet in 2006. It has a thin nitrogen atmosphere and complex geology. New Horizons spacecraft flew by Pluto and revealed surprising complexity. The Oort cloud is even more distant, a spherical shell of icy bodies surrounding the solar system. Comets originate from the Oort cloud. No spacecraft has reached the Oort cloud. It's so distant that reaching it would take thousands of years with current propulsion. Exploring these distant objects is far future vision. Now let me discuss the challenges of establishing settlements at different locations. On the Moon, the main challenges are radiation exposure. The Moon has no magnetic field or thick atmosphere to shield from cosmic rays. Extreme temperature variations. Daylight side reaches 120 degrees Celsius. Night side drops to minus 170 degrees. Water access. Water ice exists at the poles. Extracting it is technically challenging. Dust. Lunar dust is abrasive and electrostatically charged. It damages equipment and clings to spacesuits. Partial gravity. 1/6 of Earth's. Long-term effects on humans are unknown. But the Moon is close, 3 days travel. This makes resupply missions feasible. Solar power is possible. The poles, while cold, receive nearly constant sunlight due to the Moon's axial tilt. Lunar bases would be partially self-sufficient, receiving supplies from Earth but producing water, fuel, and oxygen locally. On Mars, challenges are greater distance, 9 months travel time makes resupply difficult. Thin atmosphere provides some protection but not enough. Radiation remains a hazard. Dust storms. Seasonal dust storms can cover the planet, blocking sunlight for solar panels. Resource extraction. Water ice is accessible. Extracting and processing it requires engineering solutions. Partial gravity. 1/3 of Earth's. Humans can survive but with health effects. Cold. Average temperature minus 65 degrees Celsius. But Mars has advantages. Days are Earth-like in length. 24 hours, 39 minutes. Humans adapt easily. Water ice is accessible at both poles and in buried deposits. Atmosphere provides some shielding and can be processed for oxygen. Regolith contains minerals and useful compounds. Proximity to the asteroid belt makes asteroid mining accessible. Mars seems more hospitable for human settlement than other destinations. On the moons of Jupiter and Saturn, challenges multiply. Extreme distances, years of travel time. Intense radiation from planet's magnetosphere. Extreme cold, minus 150 to minus 220 degrees Celsius on surface. Exotic atmospheres or no atmosphere. Difficult resource extraction. Possible tidal heating providing geothermal energy. Potentially subsurface oceans harboring life. These settlements would be small, specialized, research-focused. Establishing them requires technology more advanced than what exists today. Now let me discuss how human bodies would adapt to different gravity environments. Earth's one gravity is what humans evolved in. Our physiology adapted over millions of years. In microgravity, no gravity, the adaptation is difficult. Fluids redistribute. Blood pools in the upper body. The heart doesn't pump as hard. Bones lose density. Without load-bearing osteocytes, bone cells, decrease bone formation. Muscles atrophy. Without gravity to fight, muscles shrink. The inner ear malfunctions. Balance is disrupted. Eyes swell. Intracranial pressure increases. After weeks in microgravity, the human body becomes significantly deconditioned. Returning to Earth after months in space is agonizing. Astronauts can barely walk initially. With exercise, reconditioning happens over weeks. On the Moon with 1/6 gravity, humans would feel light but could function. They'd adapt over months or years. On Mars, with one-third gravity, humans would feel somewhat light but function relatively normally. Children born on Mars would develop in one-third gravity. Their bones and muscles would adapt. If those children eventually reached Earth, they'd struggle with one gravity. They might never fully adapt. The same is true for moon-born and space-born humans. This suggests that long-term spacefaring humans would diverge physically from Earth-born humans. After many generations, spaceborne humans might be distinctly adapted to low-gravity environments. Their physiology, even their skeleton structure, would differ from Earth humans. This raises interesting evolutionary questions. Would space-adapted humans be a separate species eventually? Would there be cultural divergence too? Low-gravity humans with different psychology, values, culture from Earth humans? This is speculative, but it illustrates how space settlement might change humanity. Now let me discuss the psychological and social challenges of space colonization. Living on Mars means months in space followed by years on a hostile planet, surrounded by habitat walls. The psychological stress is immense. Isolation from Earth and home, confinement in small spaces, danger and risk awareness, separation from loved ones for years, inability to leave or escape, limited social interaction with a small crew, monotony and routine. These factors contribute to depression, anxiety, and interpersonal conflict. Historical polar expeditions show these effects. The Endurance expedition, trapped in Antarctic ice, saw crew morale deteriorate despite their resilience. Modern Antarctic research stations report higher rates of depression and interpersonal conflicts during winter. Submarine crews, isolated for months underwater, experience similar psychological challenges. Space missions will require careful crew selection, people psychologically suited to isolation. They'll need psychological support, communication with Earth, recreational activities, and social activities with crewmates. Crew composition matters. Mixed gender crews might be more psychologically stable than single gender. Diverse backgrounds might help. People from different cultures bring different perspectives that help prevent groupthink. Mission length matters. Shorter missions have less psychological toll. Longer missions require stronger psychological support. Training helps. Simulations and preparation reduce shock when challenges arise. But even carefully selected, trained astronauts will face psychological challenges. Managing mental health in space is as important as managing physical health. Long-term Mars settlements with hundreds or thousands of people would have more normal social dynamics. Diversity of roles, activities, and social interactions would help. Family life on Mars, children, schools, families might improve psychological well-being. But early missions with small crews will face psychological challenges. Now let me discuss the scientific research motivations for space exploration. Mars might harbor life. Searching for life is a major scientific goal. Ancient Mars had liquid water, warmer temperature, and denser atmosphere. It might have had life. If life emerged on Mars and exists there today, finding it would confirm that life isn't unique to Earth. Europa and Enceladus similarly might harbor life in subsurface oceans. Finding extraterrestrial microbial life would revolutionize astrobiology. Mars geology interests planetary scientists. Understanding Mars's geological history illuminates Earth's. Mars lost its magnetic field. How? Why doesn't Mars have a magnetic field now? Mars lost most of its atmosphere. How? What happened to the atmospheric escape? Studying Mars answers questions about planetary evolution. Studying planetary interiors requires seismic instruments, heat flow measurements, and other instruments best deployed by humans or advanced robots. Studying the surfaces requires direct observation, sample collection, and experimentation. Remote observation from orbit provides information but has limitations. Humans on the surface can do far more than robots. A human geologist can traverse terrain, make observations, collect samples strategically, adapt to surprises. Robots do the same, but more slowly and with more difficulty. This scientific motivation drives much space exploration. Beyond science, there's exploration for exploration's sake, the desire to go, see, and understand new worlds. This is ancient human motivation. We explore because we're curious. The conquest of new territories has motivated human civilization throughout history. Space exploration is this impulse extended to the cosmos. Now let me discuss potential pitfalls and risks. Space travel is risky. Missions fail. People die. The Space Shuttle Challenger exploded in 1986, killing 7 astronauts. The Shuttle Columbia burned up on re-entry in 2003, killing 7 more. The Apollo 1 cabin fire in 1967 killed 3 astronauts. These tragedies remind us that space exploration carries real danger. Future missions will have casualties. It's a risk astronauts accept. But we must minimize risk through engineering, training, and procedures. Another risk is financial. Space exploration is expensive. Investing heavily in Mars might divert resources from Earth problems. Climate change, poverty, disease. This is a legitimate concern. There's tension between space exploration and addressing Earth problems. But it's not zero-sum. Governments can invest in both. Another risk is political. If space becomes a domain of national competition rather than international cooperation, it could lead to militarization, space warfare, satellites destroying satellites, weapons deployed in orbit would be catastrophic. The Outer Space Treaty of 1967 prohibits weapons of mass destruction in space, but conventional weapons aren't explicitly prohibited. Hopefully, space remains peaceful. Cooperation is more beneficial than competition. Another risk is that colonizing space might be used as an excuse to neglect Earth. If powerful people believe space is the future, they might reduce investment in Earth sustainability. This would be foolish. Earth will remain important even if humans colonize space. Sustainable development on Earth must continue. Another risk is contamination. Bringing Earth microbes to Mars might contaminate Martian environments. If Martian life exists, Earth contamination could destroy it. To prevent this, spacecraft are sterilized. Equipment is cleaned to eliminate microbes. But complete sterilization is impossible. Some microbes survive the sterilization process. Future missions must balance exploration with protection of pristine environments. Conversely, bringing Martian material to Earth might contaminate Earth. Samples are handled carefully in sealed laboratories to prevent contamination. These risks are manageable but require care and resources. Another consideration is whether space colonization is morally justified. Some argue that humanity should remain on Earth and solve Earth's problems before colonizing space. Others argue that colonizing space is necessary for humanity's long-term survival. Others argue that exploration itself is valuable regardless of utility. These are philosophical questions without clear answers. But I think the consensus is that both Earth stewardship and space exploration are valuable. We should pursue both. Finally, let me discuss the timeline more explicitly. The next 5 years, 2026 to 2031, Moon missions resume. NASA Artemis missions land humans on the Moon. China lands Taikonauts on the moon. SpaceX Starship completes development and begins operational flights. Mars rovers continue exploration, searching for signs of past or present life. Private space stations become operational. Tourists visit these stations. Hypersonic travel development accelerates. Point-to-point Earth travel becomes possible. The following 10 to 20 years, 2031 to 2041, lunar bases are established with multiple nations and companies operating. The first crewed Mars missions launch. Humans land on Mars for the first time since Apollo. Asteroid mining operations begin. Small asteroids are processed for water and metals. Space-based power generation is tested. Satellites transmit power to Earth. Long-duration spaceflight becomes routine. Astronauts spend months in space without extreme physical deconditioning. The following 20 to 50 years, 2041 to 2071, Mars settlements expand. Thousands of people live on Mars. Bases are established on moons of Jupiter and Saturn. Interstellar probes are launched toward nearby stars. Space tourism is common for wealthy people. Manufacturing in space becomes profitable for certain products. The solar system is extensively mapped and explored. The following 50 to 100 years, 2071 to 2026, humans are born on Mars, the Moon, and in space stations. They never visit Earth. Settlements throughout the solar system are self-sustaining or nearly so. Advanced propulsion systems enable faster travel. The search for extraterrestrial life has yielded results. Microbial life is found on Mars, Europa, or Enceladus. Permanent settlements exist on most major moons. Technology has advanced beyond current recognition. This timeline is aspirational but based on current technological trajectories and funding scenarios. It's not inevitable. Setbacks, funding cuts, or disasters could delay it, but it's achievable if humanity commits to space exploration. Now, let me end with a personal perspective. When I look up at Mars in the night sky, I see a rust-colored point of light. It's barely noticeable, fainter than Jupiter, brighter than most stars. But that point of light represents an entire world. 4 millennia ago, humans watched Mars and wondered what it was. They couldn't imagine that one day humans would stand on its surface. Today, we can imagine it. We have robots there. We have detailed maps. We understand the terrain and composition. In decades, humans will be there. It's remarkable. We live in an age where reaching other worlds is transitioning from fantasy to engineering problem. The great age of exploration on Earth is over. Every continent is mapped. Every ocean is traversed. But new age of exploration is beginning. The age of space exploration. For the first time in human history, we can expand beyond Earth. We can establish homes on other worlds. We can build civilizations among the stars. It's one of the greatest opportunities in human history. I hope we seize it. Let me address specific technical challenges that spacecraft must overcome. Life support systems are critical. For a crewed spacecraft, every human needs breathable air, oxygen. Spacecraft generate oxygen by electrolysis of water or chemical oxygen generation. Water for drinking, hygiene, and humidity control. Spacecraft recycle water continuously. Food, typically freeze-dried or thermostabilized. Temperature control. Spacecraft must maintain comfortable temperatures while in space and handling external temperature extremes. Waste management, both solid and liquid waste. Early life support systems were one way. Oxygen was generated from chemical reactions. Water was brought from Earth. Modern systems are closed loop. Water is recycled. Air is purified and recirculated. Waste is minimized. The International Space Station has one of the most advanced life support systems. It recycles over 90% of water. A Mars spacecraft would need equally advanced systems. 8 months to Mars, a year on the surface, 8 months returning, 2 years total requiring life support. The system must be reliable. If water recycling fails mid-journey, the crew dies. Communication is essential. Spacecraft must communicate with Earth too. Receive commands from mission control. Transmit telemetry, data about spacecraft health. Transmit scientific data. Enable crew morale through personal communications. Communication uses radio signals traveling at light speed. Earth-Mars communication delay is 3 to 22 minutes, depending on orbital positions. This means that real-time communication is impossible. Commands sent to Mars arrive after some delay. Responses arrive after more delay. Mission Control sends commands. Mars rover or crew waits for them, executes them, reports results. This delays operations but is manageable. Power systems are critical. Spacecraft need electricity for life support, communications, scientific instruments, and propulsion. Power options. Solar panels. Work well near Earth and Mars. Less effective in outer solar system. Radioisotope thermoelectric generators, RTGs, use heat from radioactive decay to generate power. Work anywhere but produce limited power. Fuel cells. Chemical reaction produces electricity and water, used on Apollo missions and Space Shuttle. Nuclear reactors, theoretically excellent but complex, heavy, and politically sensitive. For Mars missions, solar panels and backup power systems are planned. Navigation is challenging. Spacecraft must follow precise trajectories to reach destinations. Earth-based navigation tracks spacecraft position using radio signals. Tiny adjustments correct trajectory. A small error early in the journey can result in missing Mars by thousands of kilometers. Navigation requires careful planning and constant monitoring. Heat management is critical. Spacecraft absorb heat from the sun. Onboard equipment generates heat. Excess heat must be radiated to space using radiators. In cold regions, deep space, keeping warm is difficult. Spacecraft use insulation and heaters. During Mars entry, the spacecraft heats up from friction. Heat shields protect the interior. Temperature control systems are complex and critical. Life support, communication, power, navigation, and heat management are just 5 critical systems. A Mars spacecraft has dozens of systems, each critical. Redundancy is essential. If one system fails, backup systems take over. Training crews to handle emergencies is extensive. Now let me discuss the role of artificial intelligence and robotics in space exploration. Robots are already central to space exploration. Mars rovers like Curiosity and Perseverance explore Mars, drill rocks, analyze samples, and transmit data. Humans can't be on Mars continuously with current missions. Robots do the exploration. Future crewed missions will have human explorers supported by robots. Robots could prepare habitats before humans arrive, conduct dangerous explorations, assist with construction and mining, perform repairs and maintenance, collect and process samples. Artificial intelligence enables robots to make decisions without waiting for Earth commands. An AI-powered robot can navigate terrain, make decisions about where to go, what to sample. Humans would provide overall direction. Robots would handle details. This partnership, humans for strategy and creativity, robots for execution and reliability, is powerful. As technology advances, robots become more capable. Eventually, robots might be as capable as humans at exploration, but humans bring intuition, creativity, and the ability to make novel decisions in unexpected situations. Humans plus robots is better than either alone. Now let me discuss the costs more concretely. The Space Launch System, SLS, costs roughly $2 billion per launch. A single Starship launch, when fully operational, might cost $5 to $10 million. The difference is dramatic. SLS is government funded, expensive. Starship is commercial, cost optimized. Starship's low cost enables multiple launches. Multiple launches mean more payload to space. A Mars mission might require 10 to 20 Starship launches to assemble a spacecraft in orbit. At $5 to $10 million per launch, that's $50 to $200 million for launch costs alone. Add spacecraft development, $50 to $100 billion, crew training, $1 to $5 billion, mission operations, $5 to $10 billion, and costs approach $100 to $200 billion. This is expensive but manageable for wealthy nations or consortiums. For comparison, global military spending is $2 trillion plus annually. Space exploration costs are less than 0.1% of that. The question is not whether humanity can afford space exploration, but whether it's a priority. If space exploration is a priority, funding is available. If other priorities take precedence, space exploration stalls. Now let me discuss the long-term vision from a different angle. Some futurists propose that humanity's future depends on becoming a multi-planetary species. The argument is that Earth faces existential risks. Nuclear war could destroy civilization. Climate change could make Earth uninhabitable. Asteroid impacts could cause extinction. Engineered pathogens could be released. Artificial intelligence could pose risks. Any of these could end human civilization. If humans exist only on Earth, any civilization-ending event means human extinction. If humans exist on multiple planets, a catastrophe on one world doesn't end humanity. Therefore, establishing human settlements on Mars, the Moon, and beyond is essential for humanity's long-term survival. This is the backup Earth argument. It's compelling. Having multiple settlements ensures humanity survives. But it's also used to justify prioritizing space over Earth problems. The counterargument is that we should focus on preventing catastrophes on Earth rather than planning to escape. Climate change, nuclear war, and other existential risks should be addressed directly. Space colonization is expensive and doesn't solve Earth problems. My view is that both are important. We should pursue both Earth stewardship and space exploration. They're not mutually exclusive. Now let me discuss the cultural implications. If humans colonize Mars, societies will be different. A Mars colony might develop distinct values, culture, and identity. They might call themselves Martians, not humans from Earth. They might develop distinct laws and governance. They might develop distinct religions or philosophies. Over generations, Martian humans might diverge from Earth humans culturally and possibly biologically. This raises interesting questions. Would Martian humans be a separate culture, a separate nation, a separate species? Would there be conflict between Earth and Mars? Would Mars eventually declare independence from Earth? These are long-term questions, but worth considering. Similarly, humans born in space might develop distinct cultures. Space-born humans might have different values from Earth-born humans. As human civilization spreads, diversity increases. This could be healthy, different perspectives and cultures, or it could lead to conflict, competition between Earth and space civilizations. How this plays out depends on values, governance, and communication. Hopefully, a common human identity would transcend planetary or space origins. Now, let me discuss the environmental impact of space exploration. Launching rockets produces emissions. Rocket exhaust contains water vapor, carbon dioxide, nitrogen oxides, and soot. A single Starship launch produces roughly 300 tons of exhaust. This seems small compared to global emissions, but it adds up. If space launches increase dramatically, emissions could become significant. Research is ongoing to develop more sustainable rocket fuel. Methane-based fuel, used by Starship, is cleaner than traditional rocket fuel. Hydrogen-oxygen fuel, used by SLS, produces water vapor exhaust. Electric propulsion and solar sails would have zero emissions in operation. As space launches increase, developing clean propulsion becomes important. Another concern is debris in space. Defunct satellites, rocket stages, and collision fragments orbit Earth. There are millions of pieces of debris, some traveling at extreme speeds. A piece of debris could collide with a spacecraft, causing catastrophic damage. This Kessler syndrome scenario, cascade of collisions creating more debris, is a long-term concern. Mitigating debris requires designing satellites that deorbit at end of life, removing defunct satellites from orbit, avoiding creating debris from collisions. This is an active area of research. Impact on Earth ecosystems is minimal currently, but if space launch increases, upper atmosphere pollution could become an issue. These are manageable challenges requiring attention but not prohibitive. Now let me address the question, what if humans encounter aliens? The probability is low. The universe is vast. The distances between stars are immense. If we eventually reach other star systems, we might find planets with life. If we find intelligent aliens, first contact would be extraordinary. How would we communicate? What if they're hostile? What if they're vastly more advanced? These are speculative questions, but fascinating. The famous Drake equation attempts to estimate the number of intelligent civilizations in the galaxy. N equals R times F, P times N, E times F, L times F, I times F, C times L, where N equals number of intelligent civilizations, R times equals rate of star formation, Fp equals fraction of stars with planets, and in E equals number of planets per star in habitable zone, Fl equals fraction of habitable planets with life, Fi equals fraction with intelligent life, Fc equals fraction that broadcasts signals L equals lifetime of civilization. Estimates vary wildly. The equation produces numbers from only one civilization, ours, to billions of civilizations. The key unknowns are how often life arises, how often intelligent life emerges, and how long civilizations persist. If intelligent life is rare and civilizations typically last centuries, then intelligent civilizations are separated by thousands of light years and thousands of years. First contact becomes almost impossible. If intelligent life is common and civilizations last millions of years, the galaxy might be teeming with intelligent species. We don't know which scenario is correct, but given the vastness of space, first contact is unlikely in the next few centuries. Now let me address a question about Mars specifically, whether it's even worth colonizing. Mars is the best candidate for human settlement in the solar system, but it's not ideal. The gravity is only 1/3 Earth's. Long-term effects on human health are unknown. The radiation is dangerous. Cosmic rays reach the surface due to lack of magnetic field. The atmosphere is unbreathable. Temperatures are extreme. Water is locked in ice deposits requiring extraction. Dust storms are common. Solar power might be blocked for weeks. Days are slightly different from Earth's, causing circadian rhythm disruption. The psychological challenge of living in an isolated habitat for years is severe. Why colonize Mars then? Because Earth is the only planet we know with life. Because understanding whether life exists on Mars informs our understanding of life's prevalence in the universe. Because establishing a second civilization ensures humanity's long-term survival. Because the challenge of colonizing Mars inspires human achievement. Because Mars represents the frontier, the next frontier for human exploration. These reasons are compelling even if Mars is difficult. Humans have always pushed into challenging frontiers. Deserts, mountains, polar regions, oceans. Mars is the next frontier. Difficulty doesn't deter explorers. It motivates them. The very fact that Mars is challenging makes it worth the effort. Let me discuss some fascinating scenarios that researchers and futurists have imagined. The generation ship concept involves a massive spacecraft designed for multi-generational journeys. Imagine a spacecraft the size of a small city. It has agricultural areas growing food. It has residential areas where thousands of people live. The ship has recreational areas, schools, hospitals, manufacturing facilities. Inside the ship, a complete ecosystem mimics Earth's conditions. People live their entire lives aboard the ship. They're born, grow up, have children, grow old, and die aboard. Their children and grandchildren continue the journey. After centuries of travel, descendants reach their destination. This concept appears in science fiction, but is technically feasible. The challenges are maintaining the ship over centuries, keeping the crew motivated across generations, and ensuring the technological infrastructure persists. Would humans willingly board a ship knowing they'll never reach the destination? Would their descendants maintain the mission? History suggests it's difficult. Few people willingly sacrifice for benefit of distant descendants, but some might. People with strong ideological commitment might board a generation ship. Religious groups might colonize space based on faith. Governments might mandate generation ship missions for population dispersal. Eventually, generation ships might transport millions of humans between star systems. Another fascinating scenario is terraforming planets for human habitation. I mentioned Mars terraforming earlier, but let me discuss it more deeply. The process would take centuries. First, you'd warm the planet, either by releasing greenhouse gases or by deploying orbital mirrors. As Mars warms, its atmosphere thickens. Carbon dioxide ice at the poles sublimes, adding to atmosphere. Gradually, surface temperature increases. Liquid water becomes possible. Then, you'd introduce organisms to change the environment further. Extremophile bacteria would break down rock, creating soil. Lichens and mosses would colonize the surface, producing oxygen. Eventually, algae and plants would grow. They'd produce more oxygen. Over centuries, Mars would become increasingly habitable. But complete terraforming might take millennia. It's an extremely long-term project. Another scenario is creating artificial environments inside planets or moons. Dyson spheres, hypothetical megastructures surrounding stars, are far future concepts. A Dyson sphere would capture the star's entire energy output, supporting trillions of inhabitants. Building a Dyson sphere would require resources from billions of asteroids and probably wouldn't be completed for millions of years. But it's theoretically possible. On a smaller scale, humans might create rotating space habitats providing artificial gravity. A Stanford torus is a rotating cylindrical habitat. Rotation creates centrifugal acceleration, simulating gravity on the inner surface. Humans living in the torus would experience artificial gravity Without the biological challenges of low-gravity planets, habitats could contain millions of people, complete ecosystems, and Earth-like conditions. These are far future concepts, but they illustrate the scope of what might be possible. Another scenario involves uploading human consciousness to computers and existing as digital beings. If human minds could be uploaded to computers, they could experience space exploration without biological limitations. Digital beings could travel at light speed without aging, exist in any environment without physical protection, be copied for instant colonization of multiple worlds, live indefinitely. This is deeply speculative. We don't know if consciousness can be digitized or if uploaded minds would be really us. But if possible, it would transform space exploration. Another scenario is artificial superintelligence exploring space without humans. If artificial intelligence achieves superintelligence, it could be far better at space exploration than humans. Superintelligent AI could solve difficult engineering and physics problems, make optimal decisions with vast computational power, travel at high speeds with advanced propulsion, adapt to any environment. AI might explore space and terraform planets while humans remain on Earth or in space habitats. This raises questions. Would AI exploration still be human exploration? Would we count it as human achievement? These are philosophical questions without clear answers. Finally, let me discuss the possibility of discovering ruins or evidence of previous civilizations in space. What if Mars once hosted an advanced civilization that subsequently collapsed? Archaeological evidence would be extraordinary. We'd learn about an alternative history of technological civilization. We'd learn what causes civilizations to collapse. We might recover advanced knowledge from ruins. This is pure speculation. We have no evidence that Mars was ever inhabited by intelligent life. But if it were, the scientific implications would be profound. Or what if we discover evidence that humans are not native to Earth? Some fringe theories propose that humans were seeded by aliens or come from other worlds. These theories have no scientific evidence, but they're fascinating to consider. If evidence emerged that humans originated elsewhere, it would revolutionize our understanding of human origins. Again, this is speculation without current evidence. But space exploration might reveal surprising truths about human origins and the universe's history. Now let me return to the practical reality and offer final thoughts. The next decade will determine the trajectory of human space exploration for the coming century. Will governments commit to Mars missions? Will private companies succeed in reducing launch costs? Will international cooperation advance, or will nationalism dominate? Will technology develop at expected rates, or will unexpected breakthroughs accelerate progress? The answers to these questions will shape the 21st century and beyond. If we're bold, humans might establish thriving settlements on Mars within 50 years. If we're cautious, Mars colonies might take 100 plus years. Either way, the vision is compelling. The next generation of humans will remember who first walked on Mars, just as we remember Neil Armstrong. They'll know the names of the first Martian colonists. They'll study the history of space exploration as a crucial turning point in human civilization. Space exploration is one of humanity's noblest endeavors. It represents our best impulses: curiosity, courage, cooperation. It demonstrates what humans can achieve when we work together toward ambitious goals. It expands our knowledge and understanding of the cosmos. It ensures humanity's long-term survival by spreading to multiple worlds. It inspires future generations to pursue science, engineering, and exploration. For all these reasons, I believe space exploration is essential. The frontier awaits. The universe is calling. Humanity's story continues, not confined to Earth, but spreading among the stars. Let me take a moment to address some questions that people often ask about space exploration. How long can humans survive in space? Without any life support, humans would lose consciousness in seconds and die in minutes. With a spacesuit, humans can survive in space indefinitely if the suit is maintained. On the International Space Station, astronauts survive for months in orbit. In theory, humans could survive in space for years if properly equipped and supported. How much does it cost to send one person to space? Currently, it costs roughly $1 billion per astronaut when accounting for spacecraft development, training, and mission costs. This is expensive, but as launch costs decrease, per astronaut costs will drop. Eventually, space tourism might cost hundreds of thousands of dollars per person, expensive but accessible to many. Will humans need to genetically modify themselves for space? Probably not in the near term. Current humans can adapt to space environments with technology and training. Long-term genetic modifications might enhance space adaptation. But this is far future speculation. Why haven't we gone back to the moon since 1972? Political priorities changed. The space race was won. Funding was redirected. Technology didn't fundamentally prevent returning. Political will did. Now that multiple countries and private companies are interested, returning to the moon is happening. Is Mars really habitable for humans? Mars is habitable only with extensive technological support. Humans can't survive on Mars' surface without spacesuits and habitats. But Mars is more habitable than other planets. It has water ice, moderate radiation, reasonable temperature, soil. With enough technology, humans can establish settlements on Mars. Will space exploration cause irreversible environmental damage? Space launch produces emissions, but the total is small compared to other human activities. Debris in orbit is a concern, but manageable with proper practices. Overall, space exploration's environmental impact is minimal. It's not a major environmental threat. How will space exploration affect religion and philosophy? If life is discovered on other worlds, religions might reinterpret teachings to accommodate extraterrestrial life. Philosophically, human uniqueness might be challenged, but humanity's value would remain significant. Space exploration might inspire wonder and reinforce belief in cosmic mysteries. Or it might support materialism and empiricism as the foundation of knowledge. These are personal interpretations. Can we terraform Venus or Mercury? Venus's extreme heat, pressure, and toxic atmosphere make terraforming extremely difficult. It would be harder than Mars. Mercury's extreme temperatures and radiation make it inhospitable. Terraforming seems impractical. Other moons like Europa or Enceladus have subsurface oceans that interest scientists, but are harder to terraform than Mars. Mars remains the most practical terraforming target. Will space exploration militarize space? Possibly. Nations developing space capabilities might weaponize space, but the Outer Space Treaty prohibits weapons of mass destruction in space. International cooperation and agreements might prevent space militarization, but it remains a risk to manage. What's the farthest humans have traveled from Earth? The moon is the farthest destination humans have reached, roughly 380,000 kilometers away. Apollo astronauts traveled to the moon and back. Future crewed missions to Mars will go much farther. But humans haven't left Earth orbit except for the moon. How fast can spacecraft travel? Chemical rockets reach speeds of tens of thousands of kilometers per hour. Ion drives achieve higher speeds but take longer to accelerate. In theory, future spacecraft might achieve fractions of light speed. Currently, no spacecraft approaches light speed. The Parker Solar Probe reaches 600,000 kilometers per hour near the Sun, only 0.2% light speed. Reaching other star systems requires far faster speeds. Will humans live on planets besides Earth eventually? Almost certainly yes, if civilization persists. Spreading to other worlds is a logical long-term goal. Whether it happens in decades or centuries depends on resources and priorities, but it seems likely that humans will eventually settle Mars, the Moon, and possibly other worlds. Now let me offer some final reflections. Space exploration represents humanity's highest aspirations. It represents our desire to explore, discover, and understand. It represents our technological achievements and our ability to solve difficult problems. It represents our hope for the future and our willingness to invest in long-term goals. It represents our desire to ensure our survival and expand our civilization. Every human shares this legacy of exploration. Our ancestors explored new continents, new oceans, new frontiers. We continue this tradition by exploring space. The astronauts who travel to Mars, the scientists who study distant worlds, the engineers who build spacecraft, all are participating in humanity's greatest adventure. I believe space exploration will be remembered as one of humanity's defining achievements. Future humans living on Mars or orbiting Jupiter might look back at the early 21st century as a turning point. That's when humans first left Earth for other worlds. That's when space exploration began in earnest. The decisions we make now, whether to invest in space, what technologies to develop, how to cooperate internationally, will shape that future. We have an opportunity and responsibility to invest in space exploration. The future of humanity might depend on it. Let me discuss one more fascinating aspect: the search for biosignatures on other worlds. When we explore Mars and ocean worlds, we'll be searching for signs of life. Biosignatures are indicators of biological activity. They might be atmospheric composition. On Earth, the atmosphere is filled with oxygen produced by photosynthetic life. Finding oxygen on another world would suggest life exists there. Organic molecules. Carbon-based molecules are signatures of life. Finding complex organics on Mars would suggest past or present life. Geological features. Life transforms landscapes. Stromatolites are layered structures created by bacteria. Microbial mats change surface appearance. Fossil impressions record organisms. Isotope ratios. Living organisms preferentially use lighter isotopes during photosynthesis and metabolism. Carbon-12 enrichment in samples could indicate biological processing. Spectroscopic features. Different molecules absorb and reflect light differently. Telescopes might detect spectroscopic signatures of photosynthetic pigments on exoplanets, methane and other gases. Microbes produce methane, ammonia, and other gases. Detecting these in planetary atmospheres could suggest life. The challenge is distinguishing biological signatures from chemical processes that mimic biology. Abiological chemical reactions can produce organic molecules. Geological processes can create structures resembling stromatolites. Isotope ratios can shift through non-biological processes. So finding biosignatures requires multiple lines of evidence confirming biological origin. When humans explore Mars, they'll collect samples and search for these signatures. They'll study geological features directly, making observations that robots can't. They'll conduct experiments testing whether samples contain living organisms. They'll drill deep into Mars, searching for subsurface life. The first discovery of life on Mars would be revolutionary. It would answer the question, did life arise independently on multiple worlds? If life is found on Mars, scientists would investigate whether it shares common ancestry with Earth life. If Mars life is completely distinct, it suggests life arises readily. If Mars life is related to Earth life, it might have transferred via panspermia, transfer of organisms on meteorites between worlds. The discovery of extraterrestrial life would reshape our understanding of biology and the universe's abundance. Now let me discuss specific equipment that astronauts will use on future missions. Advanced spacesuits will allow longer, more productive surface exploration. Future suits might include articulated joints reducing mobility restrictions, integrated thermal regulation maintaining comfortable temperature, redundant life support systems with extended operation time, communication integrated into suit, power systems running equipment inside the suit, integrated tools for sample collection and analysis, display systems showing data and communication. Future suits might be more like spacecraft than current suits, high-tech protective enclosures rather than fabric layers. Mobility aids might include exoskeletons giving astronauts superhuman strength, or pressurized rovers allowing longer, more distant exploration. Habitat modules will be modular, expandable structures. Early bases might be simple domes or cylindrical habitats. Later settlements would have multiple modules connected by tunnels. Modules would include living quarters with sleeping areas, hygiene facilities, common areas, laboratory modules for scientific research, agricultural modules for growing food, power generation modules with solar panels and possibly nuclear reactors, storage modules for supplies and equipment, manufacturing modules for producing equipment and supplies locally. Habitats would protect inhabitants from radiation, extreme temperatures, low pressure, and toxic atmosphere. Rovers would be vehicles for exploration and transportation. Early rovers might be pressurized for crew safety. Later rovers might be unpressurized with astronauts in spacesuits. Rovers would have wheels or tracks for terrain navigation, cargo capacity for sample collection, communication systems maintaining contact with base, life support reserves extending operating range, science instruments for analysis, mining equipment for resource extraction. Now let me address the timeline realistically. 2025 to 2030. Moon missions resume. NASA Artemis program lands humans. First reusable rocket fully operational. 2030 to 2035. Lunar base established. Private space stations operating. Mars orbit missions launched. 2035 to 2040. Humans land on Mars. First Mars base established. Moon mining operations begin. 2040 to 2050. Mars settlements expand. Moons of Jupiter explored robotically. Space-based industry develops. 2050 to 2075. Multiple Mars colonies with thousands of people. Bases on Wasselt, multiple moons. Asteroid mining profits increase. 2075 to 2100. Solar system extensively settled. Interstellar probe missions launched. Space civilization outweighs Earth's population in economic activity. 2100 to 2200. Interstellar settlements established. Multiple star systems inhabited. Advanced propulsion systems enable faster travel. Technology barely recognizable to us today. This is aspirational but based on technological trends and funding scenarios. Setbacks could delay it centuries, breakthroughs could accelerate it, but this trajectory represents plausible human expansion into space. The remarkable thing is that this expansion seems inevitable. Humans are explorers. We explore because it's in our nature. Even if governments cut funding, private individuals and organizations would eventually explore space. Even if one nation abandoned space, others would continue. Space exploration might slow or accelerate, but it seems likely to continue. Over centuries and millennia, humans will spread throughout the solar system. Eventually, humans will reach nearby stars. And perhaps, far in the future, humans will explore the galaxy and beyond. This is the long arc of human history: expansion from a single region to a continent to a world to the solar system to the galaxy. It's an epic narrative spanning millennia. We're living in the opening chapters, the point where humanity transitions from planetary to spacefaring civilization. It's an extraordinary privilege and responsibility. Let me close with one more reflection. When I consider space exploration, I'm struck by the audacity of it. We're planning to send humans to Mars, a planet 250 million kilometers away, hooked through the vacuum of space to land on a hostile world and survive there for years. It's absolutely insane. And yet it's also the most rational, necessary, and inspiring thing humanity could do. It shows our capability. It shows our ambition. It shows our refusal to be limited. The astronauts who undertake these missions will be heroes in the truest sense. They'll face genuine danger. They'll sacrifice years away from loved ones. They'll endure hardship and isolation, but they'll expand human knowledge. They'll advance human civilization. They'll inspire billions. Their grandchildren might be born on Mars. Those Martian children might think of Earth as a distant historical homeland. They might look up at the night sky and see Earth as a faint blue dot. And they'll know that their ancestors had the courage and vision to reach for a new world. That's what space exploration is really about. Not just spacecraft and technology, but human courage and vision. It's about who we are and who we can become. It's about pushing boundaries and reaching for the impossible. It's about the eternal human drive to explore, discover, and expand. As I look at Mars in the night sky tonight, I see not just a planet, but a destination humanity will reach, a destination that will change us forever. And I'm grateful to be alive in the era when that journey begins. Now, let me touch on some technical details about specific propulsion systems that scientists are considering. Solar electric propulsion is already in use on some spacecraft. These systems use solar panels to power electric thrusters that emit ionized gas at high velocity. Solar electric propulsion is efficient but produces low thrust. It's better for cargo missions than crewed missions. Hybrid rockets use solid fuel and liquid oxidizer. They combine some advantages of solid and liquid rockets. SpaceX is developing Raptor engines burning methane and liquid oxygen. These engines are reusable and powerful. The ISP of methane oxygen is around 375 seconds. Not the highest, but very reliable. Hydrogen oxygen engines achieve higher ISP around 450 seconds, but are more complex. Future engines might achieve higher performance through advanced combustion, materials, and designs. Now about the role of international space agencies. The European Space Agency operates Ariane rockets launching satellites and spacecraft. ESA is developing the Vega rocket for small to medium payloads. ESA cooperates with other agencies on Mars exploration and other missions. Russian space agency Roscosmos operates Soyuz rockets and operates the Russian segment of the ISS. Despite geopolitical tensions, Russia remains involved in space cooperation. Indian Space Research Organization, ISRO, operates satellites and rovers on a limited budget. ISRO has achieved Mars orbit and demonstrated capable spacecraft. Indian space program is cost-effective and gaining capability. Japanese space agency JAXA operates rockets and spacecraft, including asteroid missions. Canadian Space Agency contributes robotics and technology to ISS. Private companies increasingly supplement government agencies. This global effort advances space exploration through combined resources and perspectives. Now let me address philosophical questions one more time. Does space exploration diminish Earth's value? Some argue that focusing on space makes us neglect Earth, but Earth remains our home. It's irreplaceable in many ways. Space exploration doesn't diminish Earth's value. It expands human perspective. We can appreciate Earth more while also exploring beyond it. Does extraterrestrial life existence challenge human significance? If life exists throughout the universe, does humanity lose uniqueness? Some would say yes. But human consciousness, culture, science, and civilization remain remarkable regardless of whether life exists elsewhere. Finding microbial life elsewhere wouldn't diminish human achievements. Should we fear encountering hostile aliens? The probability of encountering hostile intelligent aliens is low. Even if intelligent life exists, it's probably separated by vast distances in time. If we do encounter aliens, communication might be possible before conflict. Hopefully, any advanced civilization would have moved beyond violence. Is space exploration spiritually meaningful? For many people, space exploration inspires awe and wonder. Looking at the cosmos reminds us of our place in the universe. This can reinforce spiritual beliefs or inspire secular appreciation of reality's majesty. Space exploration has spiritual significance for many. Now let me note one more practical consideration. Cost-benefit analysis of space exploration. The benefit of space exploration is difficult to quantify. Scientific knowledge, technological development, inspiration, long-term survival insurance, these are real but hard to assign dollar value. The cost is measurable. Billions annually. Is it worth it? People reasonably disagree. Some argue that resources should prioritize solving Earth problems. Others argue that space exploration is necessary and generates benefits exceeding costs. Most reasonable people acknowledge that both Earth stewardship and space exploration are valuable. The balance between them is a policy decision. Given that space exploration costs less than 0.1% of government spending globally, supporting it seems reasonable. Finally, let me note that the future is not predetermined. The scenario I've described, humans on Mars by the 2040s, settlements by 2100, is plausible but not certain. Different choices lead to different futures. If we prioritize space exploration, this scenario becomes likely. If we deprioritize it, humans might not reach Mars until much later. If we abandon space exploration, Mars might never be colonized by humans. The future depends on choices we make now. That's why space exploration matters. It's not inevitable. It requires commitment, resources, and vision. The astronauts who eventually walk on Mars will stand on the shoulders of everyone who invested in space exploration. Scientists, engineers, policymakers, educators, and inspired citizens all contribute to making space exploration possible. If you believe space exploration matters, you can contribute. Support space exploration policies. Encourage young people toward careers in engineering and science. Follow space missions. Learn about space exploration. Share enthusiasm with others. The future of space exploration depends on public support and political will. The decisions made in this decade will echo for centuries. I believe investing in space exploration is the investment in humanity's future. I believe reaching Mars is achievable and worthwhile. And I believe humanity's greatest adventures still lie ahead among the stars. Let me conclude by discussing why this moment is special. We're living in a historic transition point. For the first time, multiple nations and private companies are genuinely working towards spacefaring civilization. Previous eras had space enthusiasm but limited resources. The technology was crude. Now technology is sophisticated and costs are dropping. SpaceX demonstrated reusability works. Other companies are following: Blue Origin, Relativity Space, Axiom Space, and others are advancing rapidly. International cooperation is increasing. Nations recognize mutual benefit and collaboration. Private investment is flowing into space. Billionaires like Elon Musk and Jeff Bezos are betting their fortunes on space. This convergence, advanced technology, private investment, international cooperation, government commitment, creates an unprecedented moment. We're at an inflection point where space exploration transitions from government monopoly to broader involvement. This is healthy. Competition drives innovation. Diversity of approaches finds solutions. For young people today, space careers are genuinely achievable. If you're interested in science, engineering, physics, or mathematics, space careers are opening. The astronauts who walk on Mars haven't been born yet. The engineers who will build spacecraft are in school now. The scientists who will discover life on other worlds are just beginning their education. You could be part of this. You could help humanity reach other worlds. Even if you're not in science or engineering, you can contribute to space exploration culture, supporting policies that fund space research, advocating for space exploration, sharing enthusiasm with others. Every person who cares about space exploration contributes to its success. The path to Mars is a journey we're on together, and the remarkable thing is that this journey is just beginning. The astronauts who will set foot on Mars in the coming decades will look back and thank everyone who supported space exploration. They'll thank scientists who conducted research, engineers who built spacecraft, policymakers who funded missions. They'll thank educators who inspired students towards careers in space fields. They'll thank the public who supported space exploration and believed it mattered. Each contribution, no matter how small, helps make Mars settlements possible. When humans are living on Mars, conducting science, building communities, raising children, that will be a triumph not just for those people, but for all of humanity. For everyone who believed in the dream. For everyone who worked toward it. For everyone who supported it. Space exploration belongs to all of us. Mars belongs to all of us. The future belongs to all of us. And together, we can make the impossible possible. We can reach for the stars and succeed. Thanks for watching. I want to leave you with one final thought. When Neil Armstrong stepped onto the moon in 1969, he said, "That's one small step for man, one giant leap for mankind." That moment defined a generation. It showed what humanity could accomplish. The next giant leap will come when humans step onto Mars. That moment, when the first human boots touch Martian soil, will be equally defining. It will remind us of who we are, not just inhabitants of Earth, but explorers of worlds. It will inspire billions to dream of possibilities. It will change how we see ourselves and our place in the universe. That moment could happen within your lifetime. If you're young, you might be that person on Mars, or you might be watching when someone else takes that step. Either way, we're building toward that moment together. The spacecraft, the habitats, the rovers, they're being designed and built now. The astronauts who will go to Mars are training now. The future is being created in laboratories and engineering facilities and mission control centers. And that future includes you. It includes all of us. So as you look up at Mars in the night sky tonight, imagine it not as a distant point of light, but as a destination, a world where humans will live and work and build communities, a world that will transform our understanding of ourselves and the universe, a world that represents the best of human courage and curiosity. That world is possible, that world is achievable, and that world starts now, with the choices we make and the visions we pursue. Thanks for watching. May humanity reach for the stars and succeed. Forever onwards.